Hello, everyone. Welcome to the March 2025 Ask Me Anything edition of the Mindscape podcast. I'm your host, Sean Carroll. Before diving in to the AMAs, I want to mention two announcement kind of things. Not really announcements, two things, one announcement and one reflection, if you want to put it that way. The announcement is we have winners for this year's Mindscape Big Picture Scholarship. I hope I've been flogging this enough. Probably I haven't, but this has been going on for a few years now. It's at bold.org, so it's going to keep going on. It's not ended, so you can still contribute. We solicit donations from Mindscape listeners to help undergraduate university students achieve their dreams of studying big picture ideas down the road. So this is hosted by bold.org, which has scholarships in all kinds of things. If you go to bold.org/scholarships/Mindscape, you can find ours and contribute to it. Or you can just go to our podcast homepage, preposterousuniverse.com/podcast. In the right-hand column, there's a link that says Mindscape Big Picture Scholarship. Click on it and you get all the info. So we've been super successful. Thank you so much for contributing. We've been very successful at getting donations, so much so that each year the current plan is we can give 2 scholarships worth $20,000 each, which is not enough to send someone to college entirely, but makes a big difference to someone who's just trying to pay that tuition for school, especially if you're not planning to go in some area that is super financially remunerative down the road. And I'm very happy to announce this year's winners. One winner is Jillian Kate from, she's already a undergraduate enrolled at Auburn University, and she's studying biochemistry, biophysics, molecular biology with the goal of becoming a college professor and doing research in those areas. And one line that caught my eye from her application was that she's already planning not only to be a professor, but what kinds of courses she's going to teach as a professor. So Jillian says, my goal is to one day teach biology in a Southeastern university, and when I teach introductory courses, I hope to intertwine creativity, philosophy, and art into my lectures and course content. That certainly sounds something we could use more of in academia, so I'm all in favor of that. Other winner is Miles Webb, who is a senior in high school and looking at different universities to go to, wants to study computer engineering, material science, chemistry, and physics. And one of the lines in his application was, a dream of mine is to become the first Black Nobel Prize winner in physics. Part of me says, I hope you're not, Miles, because I hope someone else is even before you get there. But if Miles is the first Black Nobel Prize winner in physics, I hope he gives a shout out to Mindscape listeners in his Nobel Prize acceptance speech, because we have given him a little bit of a boost in paying for that college education along the way. Again, very many sincere thanks to all the listeners, because you are the ones who contribute, and it really does make a difference to students, especially in times of uncertainty when it comes to higher education, scientific research, things like that. The other announcement, which is not an announcement but a little reflection, is that in last week's episode, I did the theory of cocktails with Kevin Peterson. Bit of a change of pace, but we're allowed to have fun here at the podcast. We don't have to be serious all the time. And the thing we did at the end of the podcast, if you'll remember, is that we invented on the spot, I say we, but it was really Kevin, invented a Mindscape cocktail, the Mindscape Petrichor Negroni. Petrichor is a word having to do with that smell in the forest after it rains. So Kevin came up with a great idea, except that it was difficult to pull off for the typical home bartender. Negroni, for those of you who don't know, is 1 part gin, 1 part something Campari-esque, something bitter like that. An Amaro, I guess, in general, and then 1 part sweet vermouth, red vermouth. So the specific ingredients that matter is, what kind of gin, what kind of vermouth, what kind of Amaro do you use? And Kevin came up with Antica Formula Vermouth, which is a very standard, it's one of the ones you can easily get typically in the liquor store. It's what I generally use when I'm using that kind of vermouth in cocktails. For the Amaro, he suggested St. George Bruto Americano, which I'd never heard of. St. George I knew quite well as a gin producer, and I didn't know that they made sort of a Campari substitute, but now I do, and it's amazing. It's really, really wonderful. It's a little bit smoother than real Campari. Aperol is the other thing that people often substitute for Campari, but I like the St. George's Bruto Americano better than either one of them. So that's a real discovery. And it does have that little bit of herbaceousness in it that we were looking for in our cocktail. But then for the gin, Kevin's suggestion was to distill our own gin from vetiver, which is a type of grass that is hard to find. It's in Haiti and maybe in India, something like that. It's not easy to find vetiver. It's also not easy to distill your own gin. So I'm not at that level of cocktail wizardry. And I asked him for maybe an off-the-shelf replacement option. So he suggested Muletto gin, which I had not been aware of, and now I am. So I actually, when we did the podcast and I recorded the intro, et cetera, I hadn't made the cocktail, but now I have, and I'm here to report to you that it was very good. So the issue with the Muletto gin is the gimmick that they have. Gin is sort of flavored vodka, flavored neutral spirit of some sort, and the flavors are supposed to be various botanicals, largely juniper, but then the individual character of the gin comes from exactly which botanicals you use. And Muletto uses tomatoes, among other things, to flavor their gin. And I gotta say, I didn't say it to Kevin in the moment, but I was instantly thinking and was still thinking, that sounds terrible. Like, I like tomatoes in the right context, but in gin might not be that context. And when I got it, I managed to shake up a bottle, and it arrived. And indeed, it's not mostly made of tomatoes; it's made of some grain. But then there's a tomato essence in there, and you open it up, and it kind of smells like tomato juice. Like, it's a very noticeable tomato smell. And I was very skeptical about this, but I thought, look, he knows what he's doing. I bet this is one of those things that when you put it into the cocktail, it's not going to smell tomatoey at all. It's going to be mixed in a particular way. And indeed, that's exactly what happened. So I don't know whether I would drink Muletto gin straight. I haven't tried yet. Maybe it would be good in the right circumstances with a grilled cheese sandwich, perhaps. I really don't know. But in the cocktail, it was very good. And it did, in fact, completely satisfy the requirements of, giving you that foresty, piney, herbaceous kind of feel. In fact, maybe I could add a drop of my pine bitters that I got on the shelf there. Maybe that could juice it up a little bit. Anyway, I can give a positive recommendation to the Mindscape Petrichor Negroni. I think that it works for those of you who are into that kind of thing. I would hesitate to try to come up with a mocktail version, but it would definitely involve tomato juice somehow, which I don't know whether that would be a good thing. Anyway, many thanks as always to Mindscape listeners, especially Patreon supporters. The monthly AMA is supported by Patreon supporters. If you join on patreon.com/Sean M. Carroll, then you get ad-free versions of the podcast, and you get to ask questions for the AMAs, and you get my little tiny reflections after each episode. As usual, too many questions to answer all of them, but they're all good. Keep asking them. Someone said, can we keep asking questions even if we tried once and didn't get selected? Can we ask the same question next time? Absolutely yes. I mean, it might even slightly increase your chances of getting selected. I do try to select questions that are new to me, that I have something interesting to say about, that are relatively short, that I think will be interesting to listeners. So there's a lot of criterion that go in there, even some really good questions I can't answer just because of bandwidth reasons. But I appreciate your understanding in that matter. And with that, let's go. Julian Mark starts us off with a priority question. Remember that priority questions are ones that Patreon supporters are allowed to ask once per their lifetime, at least, their initial lifetime here on Earth. Who knows with cyclic universe models? And I will try my best to answer it. So sometimes that best is okay, sometimes it's not, but that's the risk that you run here. The question is, if I were floating somewhere between our sun and the closest star, would I be able to see my own hands? In other words, are the stars in our galaxy bright enough to illuminate any object in interstellar space, or would everything just be pitch black darkness and basically invisible, even if you're right next to it? Well, this is a question more about your ability to see, or at least as much about your ability to see as it is about astronomy. So I don't actually know the answer. My suspicion is it would look pretty dark to you. It's not that much different than just saying what do things look like if you're outside on a clear moonless night in an area where there is no artificial illumination, right? You can certainly see stars. In fact, you could see the Milky Way galaxy surrounding you. It would be kind of cool, but that's probably not enough to reflect light off of your hands and see them unless your vision just is really, really good, I suppose. That's my guess. James Heath says, I really enjoyed your solo episode on science funding, specifically when you said that the current administration is not thinking seriously about what they're cutting. Do you think we need to touch the hot stove and suffer consequences to remember why government funding of science, vaccines, alliances with Europe really matter? I want to know where this phrase of touching the hot stove came from. Like, suddenly it's everywhere on the internet. Like, I guess I can figure out what it means, but it just suddenly appeared in all my social media feeds all at once. I don't know where it came from. Well, do we need to do that? No, we should be smart enough to know that funding science, vaccines, and protecting alliances with Europe really matter. That should not be something we need to test and remember, like, oh yes, these things actually solved real problems that we faced with. All the evidence you need that the cutting is not being done in any sensible way comes from the fact that so many things have been cut and then uncut. So many people have been fired and then rehired right away. So much damage has been done and to important things with respect to health and science and national defense and national security that they're clearly not paying attention. The most recent one was they put up for sale a building that is used by the CIA for secret operations that was supposed to be secret. I mean, it's not the best secret in the world, but they just listed it for soon being sold by the General Services Administration. They're very excited about cutting things, but they're doing enormous damage. It's like saying, you have a tumor in your body, so I'm just going to start cutting things open and taking things out. Eventually, we'll find that tumor. No sensible person thinks that this is the right thing to do. And part of it is that you might think, well, if we make a mistake, we'll just fix it. But some of these things are not fixable. The United States is supposed to have a reputation as a relatively reliable international partner. All the talk about tariffs being put on and then taken off has done irreparable damage to that reputation that we've had. People in Europe and in Asia and elsewhere are absolutely realizing that they cannot rely on the United States for protection, for military support, or anything like that. So they're going to have to beef up their own defenses. And there's a certain attitude that says, well, they should defend themselves. But, as far as the United States is concerned, it really serves the United States' interest to be in charge of all that, because they might not always agree with decisions that other places make. I mean, maybe a multipolar world is better in some ways. I absolutely could see the argument for that. The real, very obvious, huge disadvantage to me is that some of these other countries are going to develop nuclear weapons. And the more countries that have nuclear weapons, the worse we all are, because the greater chance that someone uses them, either intentionally or by mistake, or they lose it or whatever. So none of this is good. It's all bad, and it's not something that's going to be easy to fix. Dennis Cooperberg says, in the big picture, a crucial claim is made. The laws of physics underlying everyday life are completely known. This strikes me as both highly plausible and surprisingly almost never mentioned elsewhere. How widely accepted would you say this claim is among physicists, or more generally among those well-versed in modern physics? Well, I've said this before, but basically, when I explain the claim to my fellow physicists, they think for about 5 seconds and go, yeah, I guess that's true. So I don't think it's something that they think about. Scientists are kind of laser focused on pushing beyond what we already know into regimes that we don't yet understand. So the typical theoretical particle physicist spends their time thinking about amplitudes or supersymmetry or branes or hidden symmetries in quantum field theory or quantum gravity or whatever it is, things that we don't understand very well. So, and also, of course, the fact that we understand the laws of physics well enough doesn't really have a huge impact on the higher emergent levels, whether it be chemistry or biology or whatever. It has some impact because you might otherwise wonder whether you're studying a chemical reaction and it doesn't happen at the rate that you expected it to. If you didn't know about underlying laws of physics, you might say, well, oh, maybe there's like a new particle or a new field somehow involved that is changing the reaction rates. That is not the way to go, given what we understand about effective field theory. So instead, people look for much more mundane chemical reasons for those kinds of things, and they find them. So I think it is something that is not controversial in the sense that there's a lot of people out there who deny it within the physics community, but it's not also something that people think about that much. And again, as I should always add, it might not be true, right? That's I always try to phrase it as, given everything we know, this is absolutely what is the most sensible thing to believe as good Bayesians. But who knows? We could be missing something deep. The most obvious thing to think about missing is something in the collapse of the wave function in quantum mechanics. I don't think that that's a very likely place to find anything new, but other people disagree about that. Rodolfo Hansen says, I've heard you speak positively about capitalism in the past. Given increasing evidence enforceable cooperative frameworks outperform their competitive counterparts, would you consider alternatives allow us to step away from the negative sum game we are currently running to a positive sum one? Well, a lot to unpack here. I don't know what that evidence is that you're pointing to, the increasing evidence about enforceable cooperative frameworks. I'm not exactly sure what is meant by enforceable cooperative frameworks. I will certainly consider alternatives. I'll always consider alternatives, but I do think a lot of alternatives are sort of influenced by wishful thinking or by unrealistic expectations. Capitalism, I think, is very, very effective at certain things, very, very harmful in other ways. And I'm in favor of fixing it and ameliorating the bad effects rather than trying something completely different until we really do get evidence that something completely different would be better. Finally, I don't quite agree with the negative sum game versus positive sum game. Like, there's no reason intrinsically why capitalism has to be a negative sum game. Indeed, I think that one could easily make an argument that standards of living and health and other very basic measures have improved over years, even for most of the less well-off people in capitalist societies. Not to undersell any of the real problems under capitalism, but there's no, again, intrinsic reason why it's a negative-sum game. The whole idea is that you incentivize people to be productive, and productivity makes everybody better off. So I think that capitalism plus a very strong taxation and social safety net system would actually be very obviously positive sum. Okay, we have two questions I'm going to group together. They're both a little vague, so maybe that's a good reason to group them together. One is from Yazan al-Hajari, who says, Kepler wrote, "Metaphors are my truthful masters. One should make good use of them. In science, metaphors shape our understanding, black holes as cosmic sinks, entropy as disorder, just as thought experiments stretch logic to reveal deep truths. Science fiction blends both, inspiring real discoveries. How do you see the role of metaphor and thought experiments in science? Are they essential tools for discovery, or should we be cautious of their limits? And has any metaphor, thought experiment, or sci-fi story ever influenced the way you think about physics?" And then Nanu asks, when you were learning physics or cosmology over the years, did you incorporate your imagination? If you did and still do, when you think about those ideas, what images does your brain generate? So to take the second question first from Nanu, I mean, yeah, you definitely incorporate your imagination. I might hesitate here because maybe you mean something different that by incorporating one's imagination than I might mean. So imagination is just a super duper important part of all of science because you're trying, as we just mentioned, to push beyond what we know, to suggest ideas for doing better than our current theoretical models do. And that is a fundamentally imaginative act. So you say, what images does your brain generate, implying that imagination is somehow associated with images in the brain. That's one kind of imagination, but there's other kind of imagination. You can imagine equations. You can imagine structural relations. connections between different parts of the physical world or something like that. So imagination is absolutely centrally crucial. And indeed, we don't understand it very well. We don't really understand how it is that the human brain comes up with hypotheses scientifically. And this is becoming a more directly relevant question in the age of AI, where you might say, well, I'm going to imagine building an AI that will do science in the same way that theoretical physicists do. And we don't really know how. We don't even really have any expectations for whether that's easy or hard or whatever. So it's becoming a very down-to-earth kind of question. For Yazan's question, what is the role of metaphor and thought experiments? It's super crucial as a matter of empirical fact. So I don't necessarily think that you need to have thought experiments or metaphor. I could imagine a kind of science that was just much more straightforward and literal, but I don't think it would be as productive, at least for we human beings. We human beings definitely think in terms of images and metaphors. I mean, one that I like to use is when I talk about Hilbert space, the space of all possible quantum states of a system. In very commonly thought of examples, Hilbert space is a vector space that is infinite dimensional. In some very realistic examples, it's still very, very big, right? 10 to the 10 to the 100 dimensional or some crazy number like that, right? So there's no possible way that any human being can actually visualize all of those dimensions of Hilbert space in their head. And yet we visualize a little bit, and we use tools like reducing the number from infinity to 3, the number of dimensions of Hilbert space, and we make a little picture of it like a 3-dimensional vector space. That's not really a metaphor. It's just a sort of a simplification. It's helpful in some ways, and it's misleading in other ways because things become different when you have a very, very large dimensional vector space compared to a very, very small dimensional vector space. But it's absolutely crucial for most of us. Others, maybe it's not crucial. Like maybe you just memorize the rules of a vector space. You say, oh, a vector is something you can add to other vectors and scale by real numbers or complex numbers or something like that. Everyone who understands vector spaces knows those rules, but what I'm saying is maybe someone only knows those rules and doesn't ever think about vectors as little arrows, right? That would be fine. You could do it that way. It's just, one less tool in your toolbox if that's the only way you're allowed to do it. I always think that science is something that benefits from a diverse set of approaches because the space of possible ideas is very, very large. And no matter how brilliant you are, if you sort of have your particular way of moving forward in the space of ideas, you're bound to miss some good ones. We're all bound to miss some good ones. And that's why you need lots of people with lots of different kinds of ideas, and you need to support them even though they're not doing things exactly the way that you want to be doing them. And that is a difficult thing to do. Anyway, that's getting off the track. Are there any metaphors, thought experiments ever influencing the way I think about physics? I mean, sure. But I would separate out those three things. Those are very different things: metaphors, thought experiments, sci-fi stories. I don't think that sci-fi stories have really influenced the way I think about physics. Maybe the closest is time travel stories that try to make everything completely logically consistent. Provide a nice way to think about that, because I do think that if time travel were possible, it would be logically consistent. It's not a major part of my scientific research, though. So most other science fiction stories do not talk about the kinds of science that I personally am invested in. For thought experiments, yes. I mean, thought experiments are everything. We're always doing sort of spherical cows, imagining if this is true, then what would happen. That's really the bread and butter of what theoretical physicists do for a living. And metaphors, it's harder. I'm always skeptical of metaphors. Many of you will know my longstanding antipathy for thinking of the universe as a balloon being blown up. That's a metaphor, right? Take a balloon, put some dots on it with a marker, blow it up, and say, oh, look, it's kind of like the expanding universe, and the dots are moving apart from each other like galaxies are, which is explaining something correctly, but also getting other things very, very wrong. In that picture of the balloon blowing up, not only do the dots get further away from each other, the individual dots get bigger. and individual galaxies don't get bigger. When you're blowing the balloon up, there is an obvious inside and outside, and in the universe there is not. So you can use metaphors, and they're very helpful, but they're also dangerous, and so you got to keep your wits about you, understanding exactly what the limitations of the metaphor are supposed to be. Mark Slight says, how should a layman understand the temperature of the cosmic microwave background radiation? Is this the temperature a thermometer in space would show if it only absorbed the microwave background and no other photons or particle collisions? Yes, that's exactly what it is. I mean, that is more or less what we measure. We have a telescope here on Earth. We have a radio telescope, right? The original one, it was in New Jersey, but now we have more advanced telescopes. But it's not that hard, if you know what you're doing, to go up on the top of a building in your random urban area in the United States and put up a telescope that can detect the cosmic microwave background. And not only do you detect photons in the radio band coming from the CMB, but you can, if you're good, measure the spectrum. And the spectrum takes the form of a black body with a certain temperature. So that's the temperature. It really is literally what you're doing. Even though there are other photons there, you build a detector that is not sensitive to the other photons, only to those in a certain direction and in a certain wavelength range, and you detect the CMB and you figure out its temperature. It's really just gas of photons bumping into you. Anonymous says, I think democracy only makes sense for groups of people who share a common ontology. If the primary concern of one group is to secure themselves an entrance ticket to a type of heaven the other group does not believe in, the minority group needlessly suffers. A decision between building a dam or an airport with a limited budget can effectively be guided by the outcome of a popular vote, whereas a decision on abortion rights hinges on whether a fetus has a soul. Given that a majority of the population is unwilling to reassess their ontological commitments, the divide often results in a hostage situation. What are your thoughts on this? Well, I think this is a real and very, very well-known problem in democracy. We've discussed it before on the podcast, the idea that a democracy is supposed to allow for people with different value systems to coexist together, but their value systems have to overlap enough to make democracy work. And, in the case of abortion or something like that, let's just try to be the more general principle here. In the case where two sets of people have very different ideas about the morality, the sort of fundamental morality of some kind of action, this is where democracy is always going to get in trouble. It's not that it can't work, right? Like whether it's abortion or the death penalty or going to war with some other country, you can personally say, look, I don't believe in the moral correctness of this. I do, however, believe in the democratic process. So what's going to happen is I'm going to accept that the democratic process has led to an outcome that I don't like, and I'm going to protest it, and I'm going to vote against it, and I'm going to try to convince other people on the other side to come to my side. But that's the best I can do because I'm part of the democracy, and I'm subject to decisions that democracy makes. So I think that is inevitable, and I think that we can easily imagine groups of people who would not work well, who would not function in a functioning democracy together. You have to imagine that the people in the democracy are committed enough to the values of democracy. There was a little plot that I just reposted on Blue Sky the other day. There was a survey of values or something like that in political parties in the Western world, or not even the Western world, in the world, I guess. And they plotted them on two axes, whether a political party was overall liberal or conservative in values, and then also the importance that a political party put on international cooperation. And, we can debate where you should be on that plot. Are you in favor of international cooperation? Are you not? Are you liberal or conservative? Are you not? That's a very much up for debate, up for grabs. That's fine. What was interesting is that they plotted different countries: the United States, the UK, Norway, Italy, China, Turkey, Russia, and they plotted where there was a functioning democracy. They plotted both what the left-leaning party, where they landed on this two-dimensional plot, and the right-leaning party. And there's a group of countries and parties grouped together that, roughly speaking, is either more liberal than conservative or at least close to neutral. And more interested in international cooperation than not, or close to neutral on that also. And it includes all of the parties, right and left, in countries that we know and love as Western liberal democracies, the European countries, Canada, or whatever, except for the right-wing party in the United States, which is off that plot, off of the group of Western democracy parties, right next to China, Turkey, and Russia, which are not democracies at all. In other words, what it's saying is the Republican Party in the United States is now closer to Russia, China, and Turkey in its political values than it is to any other party in Western liberal democracies. Okay. Now, maybe there is some room to argue about the particular methodology of that survey that they did. Fine, go ahead and do that. But the point is, one can imagine a large group of people in a country abandoning what we think of as democratic values. And I think that that's more the problem than people disagreeing about a little bit of morality because of their ontological differences. Stone R. Carroll, no relation as far as I know, says, what are your thoughts on the physical foundations of mathematics? It is interesting that the universe has produced a possibility for us to reason about these abstract mathematical objects and deduce objective truths about them. For example, to me, if Zermelo-Fraenkel axioms are true, then 1 + 1 = 2 is undeniably true. Are these truths fundamental, independent of the physical reality? Are they emergent? What's, in your opinion, the most compelling view? So I am not an expert on this stuff. I have grappled with it. I have tried to get a more nuanced understanding, but I am left unconvinced in any of the arguments either way. But so I can tell you my feelings, okay? But I'm not going to be held to saying you have to defend these feelings because I feel the force of the countervailing arguments. I'm not a mathematical realist, okay? I don't think that we should think of mathematical objects as being real, at least not in the same sense as we think about physical things as being real. So I think that physical things are real, or at least the physical world is real. We divide it up into sub-things, and that's our move, not the universe's move. And it turns out, maybe it didn't have to turn out this way, but it turns out that there are patterns inherent in the pattern in the sort of instantiation of physical reality that are describable by what we call mathematics. Okay, 1 + 1 = 2 is one way of saying that every time I have one coffee cup and another coffee cup, now I have two coffee cups, and etc. There's sort of a physical understanding of what that means. And when you get into the more wild areas of mathematics with transfinite numbers and things like that, maybe there isn't any physical instantiation of that, and maybe it sort of doesn't matter. So I think, where it really becomes, we had this conversation on the podcast not too long ago with Joel David Hampkins, so you're welcome to check that out, and a previous discussion with Justin Clark Doan that touched on these things. It is a well-known fact in, post-20th century mathematics, or I guess post-19th century mathematics, that you can easily write down axiom systems that are very similar to each other but differ in one axiom, and whether or not that axiom is there or the opposite of that axiom is there or that axiom is neither there nor not there, all of those are consistent systems, right? Like the continuum hypothesis, the existence of infinite numbers that are larger than the number of countable numbers, the integers, but smaller than the number of real numbers. Is that true or false? Well, you can choose. You can pick an axiom to include or not to include. And to me, that means clearly these things are not objectively real. There are ways that we are constructing systems ourselves that turn out to be super duper useful for discussing physical reality. For what it's worth, I do have a paper where I express these feelings. It is called Reality Realism. You're welcome to check it out. Youssef says, do you think taking more abstract math courses is beneficial for a physics student wanting to pursue higher education in physics? For example, classes like real analysis, topology, and abstract algebra. I'm curious if you think being trained in upper-level math courses is beneficial for people doing not just theoretical research, but experimental. Well, I think it's a cost-benefit analysis question. All else being equal, yes, it is absolutely useful to take those courses. It's also useful to learn foreign languages and to learn programming languages and to appreciate the history and philosophy, both of science and other things. Maybe it's beneficial to take, classes in literature or poetry because it makes you a more eloquent explainer of your science. So there's lots of things that could be beneficial. Whether or not taking a class in real analysis, for example, for those of you who don't know, real analysis is like the fancy pants way of saying calculus. But it gets very, very fancy, so you almost don't recognize it anymore. Like once you take seriously the number of numbers on the real line, things go pretty wild, and a lot of your commonsensical ways of thinking about math break down. So you have to stick with what the axioms are actually telling you, and then that's a step along the way to becoming a more rigorous mathematician. Physicists generally don't care about any of that stuff. Generally, sometimes they might, but generally you just do an integral. You're not worried too much about all the higher level details of proving that it converges or whatever. Some areas in quantum field theory, in what is called axiomatic quantum field theory, where you really try to prove careful theorems, then you need some functional analysis, real analysis, topological considerations, and so forth. But that's, a tiny little subset of physics, even theoretical physics. Like most theoretical physicists, if you want to calculate the scattering amplitude of 2 electrons into 2 photons or whatever, okay, you don't need any of that fancy math to do that. I think it's good training because it stretches your brain. It really is. Mathematics is the most rigorous. I count mathematics and sort of logic together in a set of things that say, here's a set of axioms, what can you prove? And that way of thinking is really good exercise. It's good calisthenics for your brain, okay? But the actual substance of what you learn, about some theorem, about, contractibility of a certain space or whatever, will be unlikely to be directly useful to you in your physics research. And again, it could be if you're one of those super mathematical physicists, but you're asking in general. And I think that most physicists learn the math they need as they go rather than learning math classes. And the other thing is, mathematicians are doing math for different reasons than physicists are. Physicists want to get the answer and they want to put it to work. When I was in grad school, and it dawned on me from taking quantum field theory classes, et cetera, that the idea of group theory and Lie groups and Lie algebras and representations was really important. I sat in on a class in the math department on Lie groups and Lie algebras, and it was entirely a waste of time. It was, theorem, lemma, proof, showing that something could be diagonalizable or a representation was faithful or whatever it was. And as a physicist, you would just look it up. You would just say, oh, is this true? And okay, it is. All right, I'm going to move on, right? And very elaborate methods of proving these things. So what you want out of these mathematical concepts is different as a mathematician, and that's fine. But don't think, I guess is the short answer, that you need to take fancy math classes to be a very successful physicist. Astro Nobel says, I hear a lot of people, scientists and laymen alike, talk with confidence about the existence of extraterrestrial life and the chances to find it in the near future. I have the impression that proper Bayesian reasoning is not applied most of the time, and that expectations are often mixed with hope and wishful thinking. No matter what we find or fail to find, credences are never lowered. Why are people so reluctant to admit that new results indicate that life may not exist outside the Earth at all? How should a good Bayesian reason about this? Well, I think that the thing about Bayesianism, of which I'm a big fan, is the following. You admit that you start your investigation with prior credences, right? You have priors for something being true, and then you update them when new evidence comes in. And the way that you update them is on the basis of what are called likelihood functions. Given all the different possible theories, under which theory under each theory, I should say, would the new information be probable or improbable? And, conditions under which the information you're getting is probable would increase in their credences. And that's given you your posterior, not your prior. People keep calling it a prior even after it's been updated, but that is, technically not correct. So the big worry about Bayesian reasoning is what if we start with very, very different priors, which is allowed by the rules of Bayesianism, and then you require enormous, overwhelming evidence in the form of likelihood functions to converge on a common answer. There are theorems that assure us that if we get enough evidence, we will always converge on the common answer. But you can easily find yourself in a situation where, number one, priors are very different, and number two, there's just not enough evidence to move them very much. I think that's the situation we're in right now with life on other planets. We have the fact that we exist. Some people take our existence to say you should have a prior that life is actually pretty ubiquitous, that it's easy to make, that you'll keep being told that life arose relatively quickly here on Earth, even though it might have been hundreds of millions of years, still relatively quickly compared to the billions of years that we've been around. And therefore, the argument goes, your prior should be large. Other people will say, well, I have a prior that it's very small. I have evidence that we haven't met any other civilizations yet, and that decreases my prior to an even lower number. And that's both perfectly fine. There's a lot of evidence, and none of it is definitive, I guess. I mean, there's a lot of evidence in some sense. What I mean is there's a lot of different kinds of evidence. There's evidence from biochemistry and thinking about the origin of life. There's evidence that we've looked for a lot of planets and we found a lot of planets, right? So whatever your credence is that life on other planets exist, based purely on the number of planets we've found, it's very reasonable that it should be higher now than it was before. Based on the fact that none of them have stood up and said, hi, your credence should be lower than it was before, and there's a battle going on. So I just don't think that the evidence is strong enough in any way to really be upset if people still have credences that are very different than yours. That's why I'm very, very open-minded about this particular question. The credences are just not pinned very close to 0 or 1. Chris Mason says, how do you feel about the 76ers season so far? Disappointed or as expected? So I'm not sure if Chris is teasing me a little bit here, but for those of you basketball fans out there, my team, the Philadelphia 76ers, went into the season with enormously high expectations, having two superstars on the team, Joel Embiid and Tyrese Maxey, and getting a third superstar, Paul George, as a free agent, and doing a pretty good job of building out the rest of the roster on very cheap contracts, etc. So expectations were very high, and it has been a complete unmitigated disaster. And it's a weird, it's so disastrous this season that it's almost inexplicable. It's not really that the team was ill-constructed. The obvious thing is there have been injuries, especially to Joel Embiid. I follow this too closely, so for those of you who care, Joel Embiid had a knee injury, and there's a question of how do you get better after the knee injury. He's had a lot of injuries over the year, but I think people don't quite appreciate, people who don't follow the team, don't appreciate how bizarre and unpredictable his injuries have been. Someone smashes an elbow into his face and he breaks his nose. That's not a indication that you're fragile. This is just a freak accident, and so many of these have happened to Embiid that it's kind of crazy. But the knee thing is something when you're a 7-foot-tall, 300-pound person is very worrisome. And apparently what we were told is that they went to 1 million doctors. They did all of the tests and things that they could do, and they were told that the best thing he could do to improve his knees is to play basketball. That he needs to be moving and acting, and the knees will get better. It's sort of like a workout. And so they went into the season expecting that would be true, that maybe he would have some soreness, but over time he would feel better. And it just didn't happen. He got more and more sore, and to the point where he just couldn't play basketball. And when he was playing, it was a shell of himself. A year and a couple months ago this time, Joel Embiid was playing basketball as well as anyone has ever played basketball in the history of the earth. And then he suffered this injury, and he hasn't come back. But then also, weirdly, everyone else has been getting injured also. Maxey has been injured, and George has been injured. And as a result, rather than competing for an NBA title, it looks unlikely that the Sixers will even make the playoffs this year. So I will just hold out hope. Embiid has been shut down for the year. They're going to try other different strategies for getting him better. I still I'm recognize that I am not the general manager of the team. I am not the coach of the team. I am not a player on the team. My job is to enjoy the team's success. So I'm going to continue to be optimistic that next year everyone's going to be healthy and we will dominate the league. Let's just wait for that to happen. Peter Bamber says, you recently said that for the first time you had a thought about leaving the USA as a consequence of political changes, though you have no plans to do so. What is the view amongst your friends and colleagues on this topic? Well, look, I think most people don't really want to leave their houses and their jobs, right? Especially in academia, that's super hard to do. If you're like a genius superstar, then you can call up another university and get a job offer. But most people, getting a job is very difficult and very precious, and you hang on to it when you have it, especially at a moment when funding and things like that are very precarious. It's super precarious here in the United States, obviously. The president of Johns Hopkins just put out an email, which was overall, I think, a pretty good email. Ron Daniels is the president, and he was sort of he made the point, which I hoped he would make, that we still stand up for diversity and pluralism here at Johns Hopkins. But he also said, look, we're getting cut by an enormous amount, and it might be a devastating set of cuts coming down the road, even though they don't know exactly what they are yet. As I said, because we have no idea what the actual funding cuts are going to be, so it's very hard to do planning for the future. So that kind of thing makes people worried, Certainly if I were a young person, if I were looking at postdocs and I had a chance to go to a country that was a little more reliable in their funding of science, then I would take that very, very seriously. But, as an old settled person, I'd rather, just stick around. And I think that that's basically what people think. I think that a lot of young people, we're right now, it is early March, which means that we're recruiting new grad students and things like that. Some major universities have already said we are not going to accept any new graduate students this year. Others have accepted grad students and then rescinded the offer to them because they just don't have the money. And it makes a very difficult time of a young person's life even more difficult in ways that, my heart breaks for them and I really feel bad for them. Here at Hopkins, we're thinking that we can just stick with the number of grad students that we've already accepted, so we're recruiting them. And in fact, it looks like we're going to do much better this year at getting people to come to Hopkins because we're better than average in terms of assuring the prospective grad students that they will get a position when they arrive. But if I had an option to go somewhere else that, things were more reliable, then I would take that very, very seriously. I don't yet know of any senior colleagues who are saying, I'm picking up and leaving. This is something that takes months or years to really sink in to people. So I don't think it's like that anyone will snap their fingers and suddenly we'll lose 10% of our scientists. But there's an accumulated effect that is sort of difficult to discern from moment to moment, and it's many little changes in outlook that add up to a big effect. So I don't see any exodus from the United States right now, but I think that the long-term effects are going to be very, very noticeable. Polina Vino says, do you think that agents made up of conscious agents, for example, a company or a society, can themselves have a conscious experience? What are the caveats for this, and how would we know if, say, a corporation or a country were conscious, if we can even know this? So I think I don't think it's useful to think of countries as being conscious in the same way that we human beings are being conscious for a number of reasons. I should mention that not everyone agrees. Eric Schwitzgebel, who was a previous Mindscape guest, has written a paper saying that if you are a materialist about ontology and you think that consciousness is just an emergent property, both of which are true for me, then you should probably think that the United States is conscious, which I don't think. But my reason for thinking that is not thinking that it's impossible in principle, but I think that there are questions of timescales and integration that aren't quite appreciated in most discussions of what consciousness is. When we think about consciousness, we think about not just a person contemplating themselves, we also think about their interactions with other people, right? And, people just are smaller and quicker than countries or corporations. They can have a lot of thoughts in a very short period of time. And those thoughts are kind of coherent. We know that in the brain, lots of incoherent things are going on. Lots of different parts of the brain are bouncing back and forth and interacting with each other, much like a country or a corporation. But in physics terms, you would say that the bouncing around is tightly coupled, right? Like there's part of your brain that's literally right next to the other part of your brain and very, very quickly exchanging information and coming to some equilibrium or consensus or whatever in ways that doesn't quite happen for a country or a corporation. So I think that, there are details about what is necessary to say that a group is truly conscious that tend to be absent in these dilute, large-scale things like countries or corporations. But that's more or less a feeling. There's nothing quantitative there. I'm open to the possibility. I would need some operational way of thinking about it. What is the difference that it makes to thinking about the behavior of a country or corporation to say that it is conscious or not? I think that when it comes to human beings, we invent the concept of consciousness because it is explanatory. It helps us understand how people are behaving. Oh, this person is conscious of this happening, and that's why they did this other thing. I'm not sure that talk is very useful when it comes to countries or corporations, but maybe in some circumstances it is. I'm open to the possibility. Marcin Chatty says, when I was in high school, we were told that the 19th century scientists were looking for a medium, which they called ether, in which light waves would propagate. Eventually, the theory of electromagnetism established that there was no such medium. Yet I can't help but think that the original view was vindicated by quantum field theory. Isn't the electron field of quantum field theory the equivalent of ether? No, it is not the equivalent of ether. I have answered this question or talked about it in various times, but it's been a while, so let's address it again. The fields of quantum field theory are just the quantum versions of the fields of classical field theory. So if you think that classical electromagnetism, which is a classical field theory, doesn't need ether, then you think that quantum fields don't need ether either. The point is that ether was supposed to be, like you say, a medium in which waves propagate. Whereas in contrast, field theory, classical or quantum, takes the fields as the fundamental independent entities. The waving electron field or the waving electromagnetic field or the waving Higgs field or whatever, none of these are waves in something other than themselves. Okay, so that's the ontological difference. And there's also a practical difference. The whole point of the ether in 19th century physics was to allow for there to be a rest frame with respect to which you can measure your motion, as opposed to the naive reading of Maxwell's equations, which say there is no universal rest frame. So 19th century physicists went to great lengths to sort of bend over backwards and figure out how you could reconcile the existence of a rest frame determined by the ether with the fact that you couldn't observe it in any way in Maxwell's equations. And that's how they invented things like Lorentz transformations, even before relativity came on the scene. But in quantum field theory, there's no rest frame. There's no rest frame. Everything is perfectly relativistically invariant. So the whole point of the ether is completely missing in quantum field theory. So I don't think that's an especially useful way of thinking about things. Mark Foskey says, you have said that it's wrong to think of the inside of a nucleon as a dynamic place with lots of quarks popping into and out of existence. To the best of my understanding, it's Matt Strassler who popularized that very view. Can you think of something about how a physicist could arrive at such a view and why you think it is wrong? So it's certainly not Matt who popularized that view. That view's been around forever. This is a very, very common way that physicists talk, as if the vacuum state or a particular state of a proton or neutron is actually wildly fluctuating back and forth. And I think it's just because people don't have what I would call the right philosophical view of how to think about quantum states. There's a relationship between our classical way of thinking and then what happens when we quantize it. And people kind of are reluctant to let go of that classical way of thinking. I think that if you asked any physicist, is the quantum state of a proton in its lowest energy state, is it static or is it dynamical, right? So as a literal question, there's a quantum state, psi, a vector in Hilbert space that represents a single proton alone in the universe in its lowest energy state, and just ask them, is that static or not? If they thought about it carefully, they would tell you it's static, right? So the question is that all that is going on? If you were somehow to observe what is happening inside the proton over and over again, so you make a measurement of the proton, that excites it because you're interacting with it, so it's no longer in its ground state, but okay, now you let it settle back down and you measure it again, you let it settle back down and you measure it again, or you just measure a million protons separately, each in their ground states, you would see different answers every time you measure it, because that's the nature of quantum mechanics. And there is a really strong impulse when you measure something over and over again and see it moving around from measurement to measurement, to think that it's moving around when you're not measuring it. But if you take the point of view that the quantum state is what really exists, that's just not true. So I think it's a very common view. I think that physicists have avoided talking to philosophers for a long time and haven't thought about this very carefully, but I'm going to do my part to change their minds. Tariq says, would you be able to talk about information conservation from a few perspectives to try to help clarify what information actually means in this context, particularly at the quantum level and in the context of many worlds, and why there is such a strong perspective that it must be conserved? A common example that's given is if a book is burned and you gathered all the energy, smoke, ashes, etc., ashes, etc., you could in principle reconstruct the book in all respects, binding glue all the way down to every atom and its state. If there were radioactive elements in the ink and they were decaying randomly as the book was burned, how could all this be unambiguously reversible in principle? And I don't expect such a machine to be built such that no information is lost. Yeah, I mean, when you talk about information conservation in general in physics, let's first be clear about what we mean by information, because lots of different people mean different things. I'm not going to go through all the different definitions, but the relevant one here is the data that you require to precisely specify the physical state of a system. So in good old classical mechanics, you imagine you have some number of degrees of freedom, maybe they're particles or maybe they're points of a field in space, and typically the relevant parts of information you need to specify the state are the position, the configuration of those degrees of freedom, and the momentum of those degrees of freedom, whether it's a particle or a field or whatever. In quantum mechanics, the state of the entire system is generally specified by the quantum state, the wave function, whatever you want to call it, the vector in Hilbert space. There's details there about, maybe you could think of a density operator, which indicates a distribution over possible quantum states, as more general, but that's not the point right here. We can think of everything as just a quantum state. So if you give the wave function, you've given the information. And the statement of information conservation is just that the amount of information you need to specify the state at one moment in time is preserved over time. So if I give you the equation, the information to specify the state at one moment, and I use the Schrodinger equation to evolve it forward in time, I can also go backward. The information that was in the original state is preserved. It's modified by the fact that it's evolving under the Schrodinger equation, but it's still there. If you know the Schrodinger equation, you can figure out from the future state what the past state was, okay? Now, quantum mechanics raises a complication here because there's such a thing called measurement. The way that we usually talk about quantum mechanics is there are two different ways that a quantum state can evolve. When you're not measuring it, it evolves according to unitary evolution, which is a fancy way of saying it obeys the Schrodinger equation. But when you measure it, the wave function collapses. Of course, in many worlds, you interpret that measurement event as actually just a branching of the wave function, so that the wave function as a whole just does unitary evolution. But inside a branch, which is where actually observers live, they do not see unitary evolution. They see wave functions collapsing when measurement is done. But of course, there's a more sophisticated notion of what measurement means in many worlds. It doesn't actually require any conscious being to measure it. It just requires decoherence and branching of the wave function. So Whether or not information is conserved just depends on what kind of evolution you're talking about. In the overall unitary evolution of the wave function, in many worlds, information is conserved. In Copenhagen or objective collapse models, it would not be conserved. But from the perspective of an observer in a branch, that information is completely lost because you do not see the entire wave function of the universe. So if you burn a book or burn something else in a fire and try to collect all of the information about it, and like you say, in the process, there's some radioactive decay in the wave function of the universe branches, then there is no way, in principle or in practice, for you to accumulate all the information that was in the book ahead of time. The statement is that it's there in the wave function of the universe, but that's very different than saying you can actually recover it somehow. So those kinds of thoughts experiments are always a little bit unrealistic and, in fact, are super duper unrealistic if you believe in branching of the wave function. But it's just a statement about the unitary evolution part of quantum mechanics, not a statement about measurement. Everyone knows that in measurement, information is not conserved. Nikola Ivanov says, my question is about possible information loss. See what I did there? I put these questions right next to each other because they make sense together. Possible information loss for a hypothetical observer when our universe eventually enters the phase of the de Sitter vacuum. Are degrees of freedom of the universal wave function inaccessible, hidden behind the de Sitter cosmological horizon for a hypothetical observer, or do they remain scrambled at the cosmological horizon and somehow recoverable in principle similarly to a black hole horizon? Nobody knows. That is not something that is understood. For those of you who are not familiar with this story, our universe is accelerating, as discovered in 1998, and we attribute that to dark energy pushing the universe apart. We don't know exactly what the dark energy is, but the leading candidate is simply a cosmological constant, a constant amount of energy density. And if that's true, that can stay like a constant forever, and it will push our universe apart forever, and our universe will settle down into a cold, desolate, empty state called de Sitter space, with nothing in it other than the vacuum energy, the cosmological constant, the dark energy that is pushing the universe apart. In that case, we will have a horizon around us, much like a black hole has a horizon, but in this case, we are looking at the horizon from inside, and there's no singularity associated with it. It's just a horizon in the sense that if something goes outside the horizon, then from our point of view, it can never come back. It is separated by faster than speed of light barrier. So in the context of information conservation, would it be right to think of things that are inside our de Sitter observable universe as going outside and being lost forever, or can they somehow eventually come back? I think that the simple understanding is that they're lost forever. And the real difference with the black hole case is that so there's a similarity first, I should say. For those of you who aren't familiar, both a black hole horizon and a de Sitter horizon have a temperature and they have an entropy. This is all very, very similar calculations. When Hawking and Bekenstein first figured out this stuff about black holes, Hawking and Gary Gibbons soon thereafter showed that the same kind of thing is true for the horizon in de Sitter space. So there's a temperature, there's radiation. The radiation for our real world would be very, very, very cold. If it's about 3 degrees Kelvin outside in the cosmic microwave background right now, the eventual de Sitter temperature would be something like 10 to the minus 30 Kelvin, very roughly speaking. So the point is it's much, 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 much lower. But in principle, it's there. So you might ask, can we get that information back? The difference is black holes evaporate. De Sitter space doesn't, as far as we know. So black holes don't last forever. Before we knew about black hole evaporation a la Hawking, people didn't worry that much about information loss because you say, well, I've thrown some information into the black hole. I can't get it back, but it's still in there, right? So I'm not that worried about it. Whereas once you know the black hole can evaporate, now you're like, oh, well, there's no more black hole after it's evaporated. There's nowhere for that information to be. It must have returned to us in the radiation. Maybe, maybe not. We think that that's the nice way to think about unitary evolution, as just explained. But of course, we don't know the ultimate laws of physics yet. De Sitter space, however, is forever. It's the attractor solution. It's the equilibrium solution. It's the highest entropy state the universe can be in. So as far as we know, that horizon just stays there. And there's no sense in which the information that goes beyond the horizon needs to come back to our observable universe. That's not to say it doesn't. We don't. There is an open question about whether or not we should think of de Sitter space as a finite number of degrees of freedom inside the horizon and an infinite number outside, or as a finite number of degrees of freedom inside the horizon, and everything outside is just sort of a mirage. Everything that we're thinking about as being outside the horizon is actually encoded on the horizon, and there's only a finite number of degrees of freedom to the whole shebang. Okay? We don't know, because there's lots of things we don't know about quantum gravity, holography, things like that. But I think that the easy way to think about it, until there's some strong evidence otherwise, is that the information just leaves us when it crosses the de Sitter horizon, and we're never going to get it back. It's out there, but we're never going to be able to see it ourselves. Water says, if special relativity says there is no universal now, how does many worlds know how to split? Or when to split, sorry. Many worlds is very smart. It knows lots of things. I think that this is an example where I'm going to invoke the thing that I often say, which is that the idea of branching in many worlds is made up by human beings. The laws of physics are simply that the universe obeys the Schrödinger equation. The universe is described mathematically as a wave function or a vector in Hilbert space, and it obeys the Schrödinger equation. There's nowhere in there any mention in the fundamental description of what many worlds is of branches or splits or anything like that. Those are higher level emergent phenomena. That's why David Wallace's book, former Mindscape guest David Wallace, his famous book about many worlds is called The Emergent Multiverse. And the thing about emergent things is we choose to define them by throwing away information, right? By coarse graining or whatever, by making some choices about what information matters to us and what doesn't. Typically in emergence and things like the emergence of a fluid description from a bunch of molecules, there's more or less a unique way to throw away that information to do the coarse graining. In the case of the branching of the wave function, that's not true. We can choose to let the branching happen in all sorts of different ways. So some people think that branching should be thought of as only happening inside a light cone. I'm not a big fan of that because I don't think that light cones are fundamental. I think that quantum gravity exists and you should take advantage of that. So what I like to say is you can do the branching whatever way makes sense to you as long as it's compatible with observational outcomes. In particular, in terms of special relativity, saying that different people are going to choose different reference frames, that's just a way of saying that I can do the branching differently depending on what reference frame I'm in. And the point is it makes zero difference to any observational outcome how you do the branching. There's no right way to do it. There's no implication. If I'm here and I have a spin and it's entangled with some spin very far away and I'm going to measure it, I might use a language that said, oh, the wave function of the other spin collapses now in my reference frame. But nobody cares what my now is, what reference frame I'm in, because there's no observable effect at the other spin. There eventually will be when they measure it, but that's true no matter when I do it, or even if I'm working in a frame where they measure it before me. The answers are all exactly the same. So it's completely a matter of convention how we choose to describe that branching process. Ken Wolf says, I recall you saying that you were very disappointed with the transformation of Twitter into X. What I have heard is that under X, freedom of speech was protected all but unconditionally, with protection from uncivility or downright harassment being almost entirely sacrificed as a result. Is that your experience, or was there something else at play? Well, I think there's lots going on. I don't actually spend a lot of time on X anymore, so I'm not going to trot out a whole bunch of evidence for what it's like there. But when I do go there, because I do post the new podcast every week when it comes out, it's just mess. It's just unpleasant. People are mean. People are jerks to each other. There's an enormous amount of spam and bots. And it's just not rewarding for me. There's a lot of people who are still there. And I wish that, they were on Blue Sky where I am, but that's okay. We don't need one single social media site for everybody. That's fine. On Blue Sky, I enjoy talking to people. It reminds me of what Twitter used to be. There's always jerks, right? There's always people, but it's easy to ban people and easy to block them and move on. Whereas on Twitter, that's almost all I do is block people and very rarely get constructive engagement. So I just moved over to Blue Sky, and Blue Sky for various reasons is more shielded from potential future capture by bad actors. We'll see if that's true or not, but for the moment, that's true right now. Connor Shaffrin says, I hope this question isn't too much of a bummer, but I'm just curious. How bad do you think things will get in the next 4 years? Yeah, I don't know. I've mentioned before that my track record for making political predictions used to be very good, and then starting in 2016, it became very bad. So recognizing my own limitations, I'm not about making predictions because my predictions have been pretty reliably wrong for the last decade. It could get very bad. I mean, I guess it is useful to understand, even if you don't want to make a prediction, the range of possible outcomes, right? And that includes the best possible and the worst possible outcomes. In my own personal view, I do not think that Donald Trump is a good president. I think that the things he is doing to the United States and to the world order and to the progress of science and academia are terrible and bad. If you think differently, you will obviously have different answers to this question, just so you know that that's where I'm coming from. So to me, the best possible outcome is the courts and the rest of the governmental system constrain the Trump administration from giving in to their worst impulses. They try to preserve most scientific funding, most freedom of the press and universities and so forth, all of which are under threat right now, to try to mostly, somehow or another, we don't do too much damage to our international standing and alliances. That would be the best possible outcome. And then in 4 years, people are tired of this and they throw the bums out. That seems like very, very rosy right now. I don't think it's not going to be business as usual. It's already not business as usual. Literally, as I'm recording this, they just announced that they've cut off stipends to Fulbright scholars. Fulbright scholars are, for college students who want to spend a year abroad. Sometimes they're in the United States, but they're doing something, for a year, something interesting because they won a competition and they showed that they're some of the best, most promising scholars we have. And this is their tiny salary that they pay rent on and buy groceries with, and suddenly the government says, oh, actually, we changed our mind. We're not going to give that to you. And they might be stuck in another country or something like that. This is just unconscionably bad behavior on the part of our government. And it's a very tiny thing compared to other things that they're doing, but it shows how little they care about real human beings and some of the best human beings that we have. So the worst side, the worst case scenario is that the rest of the governmental apparatus lets them go along with their plans to break everything. We essentially become pariahs on the international scene because Canada and Australia and Europe and Japan and so forth no longer think of us as reliable partners, and they form their own organizations that exclude us. The economy completely collapses because we are firing an enormous number of government workers, which leads to huge amounts of unemployment. And then we cut taxes for very rich people while not doing anything for non-rich people. And we cut Social Security and Medicaid so that very poor people are worse off. And we put on tariffs that lead to trade wars. So there's enormous inflation that we're going to have to be faced with. All of these are super plausible. They're happening, right? Like, we're not making this up right now. And potentially worse than that is that the political system will be undermined. There's this longstanding pattern where people on that side of things make a joke about something terrible and then they actually do it. And right now they're joking about getting Trump a third term in 2028. So let's just to put the fear of God into you, as it were, Trump became president in 2017, and he's become president again now in 2025. And he's the same person that he was, but the amount of damage and the swiftness that he's with which he's doing the damage, and the sort of brazenness with which he's doing the damage, has been ramped up enormously now. Back then, he was still reined in by certain expectations, right? By having certain ideas of like having regular old people in the cabinet or in government organizations. That's completely gone. Now his cabinet is full of Fox News hosts and loyalists who don't know anything about the agencies that they're leading, but they're very, very loyal to Donald Trump. So there's an enormous ramping up of the boldness and brazenness, right? Okay, keep that in mind, and then think about the fact that in 2020, he lost an election and refused to give up power. He tried his best to overturn the election results, and eventually led to January 6th, the riot taking over the U.S. Capitol. So the sensible thing to believe is that 3 years from now, so 2028, you can imagine will be as much worse than 2020 was, as 2025 right now is worse than 2017 was. So much more brazenness, so much more relying on complete control of all the levers of government and having loyalists in place. Of all the things that he's done, there's things that are very obvious, like tariffs and things like that people get worked up about. But the complete purges of independent agency leaders and people, inspector generals who are supposed to control corruption and things like that, those people are all fired, right? So the number of things he can get away with now, or in 2028, are enormously larger than what he could get away with in 2020. So that's the worst case scenario. Usually you talk to political scientists when you get like crazy political ideas in your head. You talk to professional political scientists and they talk you down. They go, oh no, it's not that bad. If you right now talk to professional political scientists, they will tell you, 90% of them will tell you, it can be much worse than you think. Like whatever crazy dream you have about democracy collapsing, the Constitution being overthrown, no more actual elections with undetermined outcomes ahead of time, all that could go. That's the worst case scenario. And I think we need to take that seriously. People are certainly talking about that. So I hope it doesn't go that bad. And, this is not even to get into measles outbreaks and other disease outbreaks and universities collapsing. We already see universities stopping letting new students in because they can't afford it, new graduate students at a lot of major universities. It's the amount of bad that it can be is really, really, really bad. So I think that even though the range of possibilities is still broad, it's prudent to plan for the worst and to see what we can do to prevent it. Justin Proctor says, I have to fly back to East to visit family soon. As someone who does a lot of traveling for work, do you feel as safe flying now after the recent cuts to the FAA and increase in collisions and near collisions as before? Well, no, certainly not as safe as before, but still pretty darn safe. I have no problems flying. Flying, until very recently, was actually super duper safe. Congratulations to the FAA and to the airline industry, et cetera. The idea of taking a giant metal bird and flinging it across the country seems a little dicey, but we don't really have air crashes anymore because we have built in an enormous amount of safety. It's much safer than driving a car or something like that. But yes, one of the very bad things that is going on right now is cutting people from the FAA, generally degrading our ability to take care of these things, shifting from well-established procedures to letting Elon Musk's company be in charge of things. It's not as safe. And I think that on the one hand, it's kind of like climate change, right? Like, that climate change is going to increase the number of unpredictable bad things happening. But when you get a specific unpredictable bad thing, you can't very easily just say, oh, climate change did it, right? You can say climate change increased the chances of that happening, but it's hard to get a very, very specific correlation there, causal relationship there. It's exactly the same thing with the plane crashes that we've seen and the close calls on runways that we've seen. It's been a little scary for some people. Some people I know personally have been in one of these situations where the plane was landing and had to actually stop landing and zoom off because there was by mistake another plane on the runway just in the last couple weeks. It's very, very difficult to directly associate these events with the degradation of the Federal Aviation Administration, but it is not surprising that the rate of those events has gone up. It's still pretty low, though. If we're honest about it, it's still pretty low right now. So I'm still very willing to hop on a plane. If it gets worse, then that could conceivably change. Chris says, at some point a few episodes back, you made an offhand comment about how the locality of physical laws was an astonishing or at least unnecessary property and could be viewed as a type of fine-tuning. I'm confused how locality can be viewed as surprising. What would a universe with non-local interactions look like? If we'd evolve in such a universe, wouldn't we have a different notion of distance such that physical laws appear to respect our idea of locality? What does distance even mean, if not the metric that determines which things can interact? Well, yeah, this is a very good question. Sorry if I wasn't clear about it before, but the important part of this question is, wouldn't you say if we'd evolve in a universe with non-local interactions, wouldn't we just have a different notion of locality such that the physical laws appear to respect those different laws? So the implication there is that given any set of interactions, it must be possible to organize them so that things interact readily when they're nearby under some definition of locality, but not when they're far away under some definition of locality. But the mathematical fact is there's no reason that that kind of organization must apply to hypothetical laws of physics. If you think about locality as we have it in the real world, given that the real world is governed by quantum field theory to a good approximation, we can sort of chop up the world into regions of space, little tiny 1 cubic nanometer regions, okay, like little boxes all over the world. And according to the rules of quantum field theory, each little box will interact directly under the laws of physics with its nearest neighbor boxes, okay? It doesn't interact directly with boxes far away at all, or even a little bit away, even 1 centimeter away. It only interacts indirectly via the boxes in between, okay? That's locality. That's what locality is. And I can easily imagine different laws of physics in which every box interacts directly and strongly with every other box. That would be entirely different than the laws of physics that we have right now, and there wouldn't necessarily be any way to organize some things such that it looked local. This is even a proven result. There's a paper called Locality from the Spectrum by Jordan Kotler et al., and they showed that a generic set of laws of physics isn't local at all. So it is sort of a mathematical fact that in the space of all possible laws, ones that admit some notion of locality are a tiny subset. Of course, you're right that the notion of locality isn't given to you by God ahead of time. If you do have some laws of physics that allow for the existence of some notion of locality, you can go and find it, right? And then you can do your best. But it's not at all something that is necessary under any possible laws of physics. Pete Harlan says, I've heard you say that effective field theories choose a cutoff for maximum energies in order not to blow up. Does anyone think that there actually is a theoretical limit on maximum energy? Yeah, sure. Plenty of theories do that. The sort of most straightforward way to do that is to really imagine that there is a smallest distance, right? That there is some minimal length scale in nature. Because you know that whenever you have a field theory, if your wavelength is shorter, the energy of the wave that you're thinking about is higher. So short wavelengths correspond to high energies. So if there's a shortest possible wavelength, there is a maximum possible energy. And plenty of approaches to quantum gravity try to do that. Arguably, loop quantum gravity tries to do that. I think that way of doing quantum gravity is not right. It takes locality too seriously, and it's not going to be able to recover holography, black hole information conservation, things like that. Now, maybe those things aren't true. So, okay, maybe that does actually work, but I think that there's good reason to think that those things are true. So relying too heavily on locality, I don't think is the way to go. But in a very different way, string theory has a kind of maximum energy because there's the Planck scale or the string scale. There's a kind of duality, and this is very vague because it happens under some circumstances but not others. But just to give you an idea, if you have string theory and there's an extra dimension in the shape of a circle, you can imagine wrapping a string around the circle, right? And you can imagine wrapping it once or twice or 3 times or whatever. Or you can imagine taking a string and not wrapping it around the circle, but letting it travel around the circle with a certain momentum. It turns out that there's a duality where you can trade one for the other. Having a string moving really fast is kind of like having it wrapped around there's some map between those possibilities anyway. So basically, I'm not doing a very good job of explaining this, but the upshot is that if you try to imagine scattering 2 strings at super duper high energy, it turns into the equivalent of a low energy interaction in some other perspective, some other point of view. It's not quite a hard cutoff on maximum energy because that probably wouldn't work anyway, but it's sort of effectively that. You can't be too naive about this because energy is not a Lorentz invariant concept. The energy that a particle has depends on the reference frame in which you're measuring it. So you have to be a little more subtle about talking about a theoretical limit on the scattering, the energy that is exchanged from one particle to another in the center of mass frame or something like that. But yeah, so you can imagine that. All of this is very far away from how we use effective field theories in the real world, because in the real world, in the sense of, actual effective field theories used to make predictions in nuclear physics or something like that, the cutoffs that we use are far, far below the Planck scale or anything to do with quantum gravity. The Great Deceiver says, I haven't heard you talk too much about the large-scale structure of the universe, filaments and supervoids and all that fun stuff. I was wondering if the galactic clustering, in terms of these immense filaments, comes out of GR and its math, or even other theories, models like inflation. Yeah, it basically does. But of course, there are details that are going to matter. The story is that we have from inflation or from some other theory of initial conditions, whatever that turns out to be, the early universe is pretty smooth, but not exactly smooth. So there are fluctuations with different amounts of noticeability on different length scales. But on every length scale, there are some kinds of fluctuations, and they're generally small in the early universe. 1 part in 10 to the 5, so 100,000th. So if there's a region of space that has 100,000 particles, the region next to it might have 100,001 or 99,999 particles, right? That's the kind of fluctuation we're talking about. And then over time, as the universe expands and dilutes, gravity pulls together matter from the slightly overdense regions by pulling matter out of the slightly underdense regions. So the universe becomes more contrasty and it becomes more lumpy in some regions, emptier in other regions. That's exactly what is predicted by general relativity plus cosmology plus initial conditions. And that's exactly what we see in the universe today. Now, the details happen because, you have dark matter and you have ordinary matter and you have magnetic fields and you have light in the universe heating things up and you have X-rays and you have supernovae exploding and injecting energy into the world around them. So the whole thing is kind of a mess. It's, what is called gastrophysics by theoretical physicists who find it a little frustrating. But having said all that, we try to do our best. We, do pencil and paper. We do simulations. We collect as much data as we can. There is right now a slight mismatch between what you predict the clustering of galaxies to be in the current universe from what we see at early times from the microwave background, etc. You make a prediction and it's not quite right. This is called the S8 tension. You may have heard of the Hubble tension. We talked to Adam Rees on the podcast some time ago. If you infer the current Hubble constant by looking at the microwave background versus if you measure the current Hubble constant directly, you get slightly different answers with a statistically significant difference. And the same thing is true for the amount of clustering. And it's called S8 because that's just S sub 8 is the number that you use to have the best constrained characterization of how much clustering there is in the current universe. Maybe it will go away when data becomes better. Maybe it's a signal that something really interesting is going on. That's why we do science, because we don't know ahead of time. David Maxwell says, your chat with Blaise Aguirre-Yarcas added to my growing impression that life at its most basic is, if not inevitable, highly likely in any environment that permits enough complexity. How have your credences changed over time? Is any Fermi paradox bottleneck at abiogenesis, multicellularity, sentience, or somewhere else? I do think that Blaise's results increased my credence that some kind of life is easier to get started or more likely to get started than you might have thought. But if you might have thought that number was incredibly small to begin with, then maybe it didn't really do a lot to update your credences. I'm actually pretty open-minded about this. I do tend to think that there are not hyper-advanced technological civilizations here in our Milky Way galaxy for the simple reason that it would have been too easy to notice them already, and we haven't. That could be wrong. There could be some reason why they're hiding from us. But it's much easier for me to imagine that they're just not there, either because life is rare or complex life is rare or something like that. But I'm open to all those possibilities. Maybe life is ubiquitous, but it never becomes complex, or just, typically it takes 1 trillion years to become complex and the universe hasn't been around long enough for that to happen. Tim Converse says, one possible explanation of the Fermi paradox is that life or intelligent life is super rare and extremely unlikely to arise. Maybe I thought of grouping these together, but just didn't pull it off. If this were true and it turned out that, say, we are the only exemplar in 10 to the 23 star systems, would it undercut a scientific approach to the origins of life that prefers likely explanations of what we see? Rarity like that would seem to open the door to Boltzmann brain-like starting events, like a large, fully formed, self-replicating chunk of RNA occurring by chance. Could a journal reviewer of the future say, if your proposed mechanisms for the origin of life or intelligent life were correct, then we would expect life or intelligent life to be common, but it is not common, so we recommend rejection? Well, yes. My general answer to the question is yes. I'm made uncomfortable by the invocation of Boltzmann brain-like things because Boltzmann brains are truly, 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 truly unlikely. You got to do the math here, and you got to say that the actual Boltzmann brains are just very, very unlikely. So I think what you mean is, in order for life to start, did there need to be something that was simply a random fluctuation that under ordinary circumstances we would think is very unlikely, but because the universe is big enough, it happened to have occurred? And yeah, I think that's absolutely a possible thing to ultimately come out as true. That's why I don't put a lot of evidentiary value on the fact that we exist here. There is truly an anthropic consideration. We wouldn't be having this conversation unless we existed. So the fact that we exist does count as evidence that life is possible, but it really gives zero impact on how likely life is. It doesn't help us distinguish between the hypothesis where life happens on 10% of habitable worlds in the universe and the hypothesis where life happens on 10 to the minus 100 habitable worlds in the universe. They're both completely consistent with us being here, so there's no evidence one way or the other. If we improve our understanding of biochemistry and geology and all of those things to say that under conditions that typically occur on a planet in our observable universe, the chance of life starting is 10 to the minus 100, then indeed, any new theory that implied that the chances were much greater than that would be counterindicated, would be ruled out, if you want to put it that way. But I don't think there's anything special about life or Fermi paradox or anything like that here. It's just saying that if your theory is making predictions that are completely violated by the world in which we live, your theory is not going to get a lot of traction. Anonymous says, have you ever had $1 million year? I just want to know that my boy Sean is securing the bag. I have not been securing the bag that well. Look, I'm doing fine. I don't want, we don't go into personal details here, but I've certainly never complained compared to many people in the world about how much money I'm making or anything like that. But $1 million in a year is not something that I have ever gotten or have ever threatened to get or ever expect to get in my life. But that's okay. You can do pretty well with less than $1 million a year. Roland Weber says, how do we know that gravity was strong near the Big Bang? Is it that a prediction from running models of the universe backwards in time and hitting singularities, or do we have direct evidence? Is that even a valid distinction, or does everything we can observe today have to be processed through models and projected back in time to tell us about the state of the universe near the Big Bang? Well, to say that gravity is strong, there's two different possible construals there. One is that as a force between two particles, gravity was stronger near the Big Bang. And that's false. At least we have no evidence of that. We have very good evidence that the strength of gravity in terms of Newton's constant was more or less the same, to within 10% of its current value a minute after the Big Bang during Big Bang nucleosynthesis. When people, including myself, say that gravity was strong near the Big Bang, what you mean is not on a particle-by-particle basis. You just mean that there's a lot more density of particles. So gravity is stronger on Jupiter than on Earth because Jupiter is more massive, not because Newton's constant is different. In the early universe, we have super-duper, practically irrefutable evidence that the density of matter was very, very high. So in that sense, gravity was just strong. You don't need anything fancy to say that that's true. You just need to understand the fact that the universe is expanding plus ordinary general relativity. Dario Kubler says, for an isotropic photon source, the received signal intensity at a given distance is modulated by the mass distribution along the optical path. This implies that the perceived brightness of distant sources, particularly at cosmological distances, may be influenced by mass distributions beyond our observable horizon, potentially impacting brightness estimations. Could this phenomenon introduce systematic errors in the standardized luminosity of type 1a supernovae, thereby affecting cosmological distance measurements and ultimately our understanding of the universe's accelerated expansion? In principle, yes, this is a very well-known phenomenon. This is gravitational lensing. There are different regimes in which gravitational lensing can happen. So there's weak lensing and strong lensing. Strong lensing is, roughly speaking, when you have a gravitating source that is so strong that it creates multiple images of a source in the background. And when you have strong lensing, the total luminosity that you're measuring can be dramatically changed by that event. But strong lensing is relatively rare. It happens, but astronomers are very happy when they see it. It leads to beautiful pictures. You can just Google strong gravitational lens, get all these multiple images, etc. But it's the rarer thing. The more interesting thing is weak gravitational lensing, which, as you might expect, is weaker, but also more ubiquitous. It's everywhere. So plenty of people have done research on asking the question, what is the effect of weak gravitational lensing on the inferred brightness of distant supernovae? The answer is not that much. It's weak, right? And it overall balances out. Sometimes you increase the brightness a little bit, sometimes you decrease it. But there's very, very strong evidence that for whatever reasons, once you apply a certain correction relative to the time it takes the supernova to increase and then decrease in brightness, type 1a supernovae at fixed redshifts all have the same brightness. So there can't be a huge effect of lensing because sometimes it would increase the brightness, sometimes it would decrease it, and that simply is not seen in the data. And that's consistent with the theoretical predictions, so I think that is pretty much under control. Rhys Johns says, could Laplace's demon know for certain what Laplace's demon would do next? No. I think maybe this isn't always clear. Maybe I don't even say it because it's just so clear to me that I don't bother. Laplace's demon doesn't live in the universe. Even if you imagine, it's just a thought experiment, it's not true, but if you imagine the thought experiment where there is a demon with a vast intelligence who knows everything in the universe well enough to predict what will happen next, you can't imagine that that demon is part of the universe, a subset of the universe, right? Because it can't have enough storage capacity in its brain to keep track of literally everything defining itself plus everything defining the rest of the world. So in any construal of what Laplace's demon is, it has to be outside of the universe. It can't be part of it. So in particular, when we say Laplace's demon knows what's going to happen next in the universe, that does not include Laplace's demon itself. Laplace's demon can't even interact with the universe because if it could, it would have to be considered to be part of it and it wouldn't be able to make those predictions. EMB asks a stupid procedural question. Is it okay when you have these AMAs to re-ask a question that you didn't pick for a previous AMA? This is a bit thorny because there's no way to know if you didn't pick it previously for time or just because it wasn't a good question. This, of course, excludes priority questions. So I mentioned this in the intro, and so I hope it's clear. Of course it's okay. You're welcome to ask whatever questions you want. Go ahead. And I might even pick them. But you're right. I do not go through all the questions that are not picked and provide explanations as to why I didn't do it. But hopefully, through my explicit instructions, plus abstracting from what kinds of questions I do pick, you can kind of get a feeling for what kind of questions get answered. It is a fine line. Like I don't answer too many super personal questions, although I did the how much money I make one just as a joke a little bit there, even though I told the truth, but it was a very vague truth. I don't, do a lot of homeworky type questions. Imagine this spaceship is going at 0.99% of the speed of light. That's just not interesting to me. Something that you can get more easily by, asking ChatGPT, I think is kind of a waste of my time. I don't. It's a weird quirk of me, and I don't want to blame anybody else, but I don't love questions that ask me about my favorite ex or the one person I wanted to meet in history or things like that. I just don't think that way. That's not how I roll. And also I don't like questions that I think I've answered many times before, or questions that are too long, or questions that are secretly trying to make an argument rather than ask a question. If you want to ask a question, your best bet is to imagine that you're having a conversation with me and you want my opinion about something, or you want a little bit of clarification that goes beyond what you could easily find on the internet. Those are the questions that I think it's most likely for me to pick. Short versions of those. Tim Giannitsos says, occasionally an academic discipline originates from a non-rigorous foundation. For example, Newton's study of derivatives and infinitesimals were not on a rigorous mathematical footing for over 100 years until the advent of real analysis, which we've already mentioned earlier, in the 1800s. However, calculus was incredibly useful in the interim. What are the most promising areas of science that you believe are worth entertaining even though they lack agreement with experiment? Well, what just happened there in the last sentence of this question? So the first part was about a rigorous mathematical foundation. Then the question at the end was about agreement with experiment. These are two very, very different things. I think that if you were to actually leaf through almost all of physics and chemistry and biology, which are all in their ways highly mathematical, almost none of them would reach the level of rigorous mathematical justification that we have in the best pure math research. Scientists just like to get to the answer, right? They like to zoom ahead without rigorous mathematical justification. Lacking agreement with experiment is an entirely different thing. I mean, I'm not going to give you a very good answer to this because the phrase lack agreement with experiment is a little bit too loose. Does that mean disagreeing with experiment? Does it mean not yet making testable predictions that we've been able to measure? Does it mean just being too vague to even talk about experiment? Does it mean having made predictions that we don't have the technology to test yet? All these are possible, and all these are going to be very different. But, I think that science is a messy thing, and we make progress by inventing theories gradually and trying to confront them with experiment as best we can. I think that sometimes people, both inside and outside, but especially outside of professional science, fetishize, unless you can tomorrow do an experiment that rules out or proves your theory, it's not worth entertaining. That's just entirely unrealistic about how science actually works. Felltrash says, do you see any silver lining in the end of the USFG as the leader of the free world? For example, I'm not sure what USFG means. I'm going to take it to be something about the United States. For example, the veil being lifted on U.S. exceptionalism. Clearly, the manner in which it's being done is unlawful, immoral, and dumb, but what good might come of it? I think it's stretching to think much good might come of it. I never believed in U.S. exceptionalism. I don't think many people believe in U.S. exceptionalism. That's the kind of thing that a politician might refer to just as sort of a speech to get hearts racing and, make people feel good about themselves. But I don't think that the world has really bought into much of an idea of U.S. exceptionalism. Correct me if I'm wrong, but that's been my impression. I think that the United States has, for a certain number of decades, served as something like a good example for a lot of countries, in the sense that we've had democratic elections, that we've been relatively materially prosperous, that we've tried to do some good things in the world, with all the footnotes that say we've done some terrible things in the world, that our democracy has been very flawed in various ways, that our prosperity has not been shared universally. All that's fine. But I do think that as an example to live up to, I would like the United States to be doing the best it possibly can. And the fact that the United States starts doing badly, I don't think that makes the world a better place. I do think that maybe it's good if other countries in the world don't rely on leadership from one particular country. A multipolar world would be good in that case. I have no special desire for the United States to be the boss of the world. Certainly, that's the last thing I want. But I don't want someone else to be the boss of the world either. And you might say I want a multipolar world, but it's hard to pull off because various countries are going to want to be the boss, right? So I don't know. I think that I would like every country to succeed and be free and democratic and prosperous, and that includes the United States as well as everybody else. Eric says, looking at websites like scaleofuniverse.com, I noticed that the interesting bits like life are roughly in the middle of the biggest and smallest things. Is there some general principle from complexity theory that would make that so? I think roughly there is. For one thing, you have to be very careful about this claim that the interesting bits are in the middle. It's a very, very rough idea, right? Because the smallest things, what do you mean by the smallest things? Do you mean an atom? Do you mean a proton? Do you mean the Planck scale? Those are very, very different in size. So it is only a very, very rough guideline. But given that, I think there are good reasons to expect that the most complex things are in the middle. On the one hand, small things just can't be that complex. There's not enough room for them to be complex. I talk about this actually in Quanta and Fields in the most recent book because of the feature of field theory that we already have mentioned. When you try to make something small in quantum mechanics or field theory, you increase its energy. Right? So if you try to do interesting things inside an atom or a proton or whatever, you can only do that by adding more energy than is already there. And that generally means that the thing just decays right away into something of lower energy. So if you're very small, and this is even true in a sort of less dramatic sense for medium small things like molecules or whatever, there just isn't that much room to have things arranged in interesting ways, to have too many moving parts, to be complex. On the largest scales, there's just simply a matter of time, as we were talking about before, for countries being conscious, right? The universe that we observe is billions of light years across. That means it takes billions of years for a signal to travel from one side to the other. There is not enough time for many interesting interactions to have happened on very large-scale things that would let you settle into some interestingly complex configuration. There's an analogous thing you can say about low entropy and high entropy. In very, very low entropy situations, you can't be complex because there's not enough room, not enough states that look that way. In very, very high entropy situations, you are in equilibrium and everything is smooth and boring. So I think it's not a rigorous theorem, but there are general reasons to expect that complexity falls in the middle of these various extremes. Jameson says, is there any reason at all to find solace in the block universe? For example, should it be a comforting thought when dealing with the death of a loved one that in some other equally real past moment of time, circumstances are different? I don't see why it would be comforting. No, I don't think that that's a source of solace. I mean, compared to presentism, I guess, I don't think that the block universe is more comforting in any way. There's a famous quote by Einstein that disagrees with me here, saying that, time is just an illusion. All moments are equally real. He was trying to console I think the widow of Marcel Grossman or something like that. But it's a bit of, rhetoric. I don't think it's very rigorous. The fact that I treat moments of the past and future as ontologically real has no impact on how I think about a loved one who has just passed away. Like, they were always in the past, they were always in the future. That doesn't provide me with much solace. What matters to me is what's going on now. I think it's better to accept what is happening in the present and what might happen in the future than to take some weird metaphysical solace in a perspective on which elements of time, which moments of time count as truly real. Rowe says, Microsoft claims to have invented a new state of matter, the world's first topoconductor. This revolutionary class of materials enables us to create topological superconductivity, a new state of matter that previously existed only in theory. Is this a real thing or is it marketing BS? I'm not an expert on the particular technology here. The experts that I know are very widely dismissive of this. And it's not that hard to see why they are dismissive of it. A paper was written by the Microsoft research team that seems to be, as far as I can tell, pretty careful. They tried to make this topological configuration that might help us build tolerant qubits someday down the road. But they said very clearly they're not sure whether they succeeded in making it. And then there was a press release that entirely, as far as I can tell, misrepresented what was in the paper, that way overclaimed what actually happened. So in between the scientists doing the work and the general public hearing about it, there was science that was done, but a certain amount of marketing BS absolutely apparently did inject itself along the way. Reese Johns says, doesn't it get boring teaching students the same material every year? Well, I haven't been teaching students the same material every year for quite a long time. In my 3 years at Hopkins so far, I've taught 6 different courses, never one repeating. Next year, I'm hoping to teach what is a repeat of my philosophy of physics course from a couple years ago. But no, even if I were teaching it the same material every year, I don't think it really gets boring. For one thing, it's a year apart. A year is a pretty long period of time. For another thing, you can continue to get better at it. You can continue to think about how to teach the material, what things to include. For a third thing, the students are different, right? So it's a different slight experience every time. So of all the things to fret about being an academic or a professor, teaching the same thing over and over again is not high on my list. Peter Newell says, in Newtonian mechanics, I would argue that the Earth orbits the Sun and not the other way around, because you can construct an inertial reference frame where the Earth basically goes around the Sun, at least on the timescale of years. However, in GR, the concept of a global inertial reference frame doesn't really exist, so the argument might break down. Here's my question. Can I make an argument valid in a GR framework simply by asserting that Newtonian gravity is the regime of GR that adequately describes the situation? Sure, you can make an argument. You're allowed to make such an argument. I mean, basically, I think that you have the right facts of what the theories are saying, but you're sort of, as I've seen other people do, clinging to the idea that, but come on, really we know that the Earth goes around the Sun. And the fact is that if you're careful about what the words goes around means, and you're careful about how we think about these things in general relativity, that is not an objectively true statement. There are reference frames in which we describe the Earth as going around the Sun, reference frames in which we describe the Sun as going around the Earth. There is also, as you point out, a Newtonian limit to general relativity, and that Newtonian limit is a very good approximation in the solar system. And there you have absolute space and time in that Newtonian regime. And you can make more objective statements like the center of mass of the Earth-Moon system, the barycenter around which things orbit, is deep within the Sun, not deep within the Earth. So there is a sense in which it is objectively true in that case that the Earth goes around the Sun. So you can concatenate these things to go from general relativity to Newtonian gravity to the sense in which the Earth goes around the Sun. Or you can just face up to the fact that we understand the universe better, and the concept of one thing in space objectively going around the other is not perfectly well defined. It's an approximation that helps us under certain circumstances. So by all means, refer to it when we all agree on what's going on. But I don't get there's an impulse, I'm not necessarily saying you have it, but there's an impulse in certain circles to sort of really insist that there has to be some objective sense in which this is absolutely true. And I think that that's not quite the right way to think about it. Rad Antonov says, in quantum fields, the approach in the early chapters is predominantly wave function focused, as opposed to matrix mechanics, commutator algebra, and operators as generators of translations or rotations. Did you adopt this approach for pedagogical reasons, or is it a reflection of a philosophical view? It's not a reflection of a philosophical view. It is the way that I think is easier to think about these things in a wide variety of circumstances. For those of you who don't know, in quantum mechanics, going back to Heisenberg versus Schrödinger, there's kind of two different ways. In fact, there's an infinite number of ways, but there's two major ways to encapsulate the dynamics of the system. One is to say I have a quantum state. That's usually the way you hear me talking, and it obeys the Schrödinger equation. So the quantum state evolves with time. And then I can do things, as you know, observationally to the quantum state. I can measure a position, measure a momentum, or whatever. And I would say that, if a particle's moving, if there's like a little wave packet that is localized and it has momentum in some direction, then if I measure it at this point versus another point, it will have moved to the left or whatever. But there's an equally good way of doing it, which is the Heisenberg kind of way of doing it, where you don't have states that evolve with time. You just have the quantum state period, but you have the operators, the observables, evolve with time. So you just, instead of saying the observable of position is a fact, it does the same thing to any quantum state, but the quantum states change. You're saying the quantum state is a fact. It is the same quantum state for everything, but the observables change. It's completely equivalent, and there's literally a mathematical procedure to go back and forth. But I do think that, especially because of how we think about classical mechanics, for me and for many people, thinking about the Schrödinger evolving quantum state way of talking about things is just more natural. So that's why I decided to talk about it that way. I'm not trying in these books, which are meant for a popular audience, to talk about every possible way of doing quantum mechanics. Hussein asks a priority question. Given the political climate that we live in, you've made it a point to dedicate time on your podcast to uplift and emphasize the importance of having an objective mainstream media for maintaining a healthy democratic society. However, over the past 16 months, my faith in the mainstream media has been significantly eroded. This has been largely due to the media's coverage of the war/genocide in Gaza. I understand that this is only one war in one place that the media is covering. However, I cannot help but separate the bias that I perceive they've engaged in their coverage on Gaza and apply it to the rest of their coverage. In short, I can't get myself to take the mainstream media as a source of authority anymore. Am I wrong in how I've reacted to the media's coverage? Well, you're not completely wrong. There's something there, but I don't ever think it should be thought of as a source of authority, right? I think that was, if the hope was that there's some media outlet that is simply authoritative and always correct and we can trust it 100%, I was just never tempted to think that way. So nothing has changed for me. The things that we think of as mainstream media outlets absolutely have their blind spots and their biases. I don't think it's very plausible to deny that that's true. But that's beside the point of whether or not we would like to have an objective mainstream media. I was not making the argument ever that the mainstream media that we have now is ideal or even all that great. I was just saying that it would be better to live in a world where there were trustworthy, objective mainstream media outlets that we could have as reliable sources of facts to the extent that that is possible. That is not something that exists. It is an ideal to which I think it is worth moving. And therefore, the thing to do is not to give up on the idea of objective mainstream media. It is to try to make the mainstream media better, more objective and more reliable. The other thing, of course, is that if you say, well, I don't like the mainstream media, what is the alternative to the mainstream media? And the answer is almost always things that are much more biased in one way or the other. You might like their biases better, and sometimes that's fine for certain specialized things, for certain sort of opinion-based things or activism-based things. It makes perfect sense to not worry about being objective and to get your information from someone who aligns with your pre-existing points of view on things. But that's, again, a separate thing, and you better admit that if you're getting all of your information from biased sources intentionally, then you're going to have to correct for those biases at some point or another. Leon Enriquez says, in episode 304, James Evans mentions abductive discoveries that come from the surprise and experimental results that experimental results can produce on a scientist. He argues, based on C.S. Peirce's ideas. By the way, if you ever see C.S. Peirce's name spelled, it looks like Pierce, but it's pronounced Peirce, I promise you. Based on C.S. Peirce's ideas, then maybe the resources for those discoveries can come from other fields different from where the surprise happens. In my musicology field, I find a lot of truth to this. Is this something you've tried successfully in your field of theoretical physics? If so, what, and if not, why? Well, yeah. I mean, you see the fruits of that attempt in the podcast that you are listening to. Part of my motivation for doing Mindscape is to be myself personally exposed to a whole bunch of ideas from a whole bunch of different corners, different fields, different perspectives, and so forth. You know, I could make a lot more money just doing a physics podcast, you know, physics news of the day, or, you know, spicy opinions about physics things. That would be more popular. There's no question about that. But it would be much less useful for me. So I want to hear and learn from all these different fields. Obviously, I'm literally a member of a philosophy department, so that is a different field that has helped me out a lot. But in different ways, there's other fields that help a lot also. So I think that it's not... To me, that's not a surprising thing. You know, the overall piece of wisdom is that the space of ideas and the space of possibilities are very, very large. And there's no possible way for a human being to think of every possible idea or to contemplate every possible possibility. We need to choose strategies for working our way through these ultimately large spaces. And one of them is to keep being jostled by ideas from outside our comfort zone. I think that's a good thing to do. Nicholas Katsantonis says, how can you explain and, if possible, conceptualize how the exchange of particles leads to attractive forces? Two negatively charged electrons exchanging photons is often analogized by imagining two people, one throwing a ball at one another and being pushed in the opposite direction by throwing, but also catching. That real-world example, in my understanding, is explained by contact forces, which themselves are related to electrodynamics and exchange of particles. So the analogy seems to be an accessible one, but nonetheless, an analogy doesn't offer a true explanation. How can we understand the exchange of particles leads to attraction, like a proton and electron coming together due to opposite electric charges? Well, it is not a very good analogy. It is, you know, it might help you a little bit, but not too much. The truth is that the force between protons and electrons in a static situation, i.e. an electron that is bound to the nucleus of an atom, is very, very difficult to understand as an exchange of particles. You can do it. There are ways to do it, but the number of particles being exchanged is infinite, and there are subtleties there. It is easier to understand it as a static electromagnetic field than as an exchange of particles. If you are scattering dynamically two particles off of each other, then it's easier to understand that as an exchange of photons. But they are virtual photons. They are not real photons. And that changes things in important ways. I talk about this also in quanta and fields. The fact that they're not real is true. They're not real, okay? They're virtual particles, which is a way of talking about the action of the underlying quantum fields using particle-like language, even though they're not real particles. And all of this is a warm-up to say, if you want to use the analogy of two people throwing a baseball back and forth to each other, the relevant baseball has to have negative momentum. So if you think about conservation of momentum, if I am on a frictionless surface or on roller skates or whatever, and I throw a ball in one direction, conservation of momentum means I move in the other direction, as long as the thing I'm throwing has a positive momentum. If the thing I'm throwing has a negative momentum, then to conserve momentum, I need to start moving in the same direction as the direction in which I've thrown the ball. And you go through the math, and indeed, for attractive forces, the virtual particles have negative momentum when they're being exchanged. And if you say, but particles don't have negative momentum, the answer is real particles don't have negative momentum, but virtual particles have no problem with that at all. Michael Kramer says, if Einstein had not developed general relativity when he did, how soon would it have been developed? Well, we don't know. I don't think it would have taken that long. Like, it wouldn't have taken 50 or 100 years. We already had all the tools, right? We had Riemannian geometry. We had special relativity. It's possible, for example, that Minkowski, to be a little bit more correct, would have developed it. Hermann Minkowski, of course, was the first to promote the idea of thinking about relativity in terms of space-time, and he was a mathematician. He had actually taught Einstein. So it was 1907, 2 years after Einstein's special relativity papers, that Minkowski first said we should think about it in terms of space-time. Einstein eventually settled on general relativity in 1915, but Minkowski passed away in 1909. So he didn't really get a chance to follow up on his insight that we should think about things in terms of space-time. Maybe he would have come up with it. But, it's an interesting fact about the progress of physics that the progress of physics on theoretical physics is usually led by physicists, not by mathematicians, with overwhelming probability. Not that it's impossible to imagine mathematicians doing it, but when we think back to how general relativity came about, and there were real mathematical issues there, and a lot of important steps were taken by mathematicians. Minkowski is one, David Hilbert, of course, is another. But still, it was a physicist. It was Albert Einstein who actually put it together, because that physics insight about the principle of equivalence and how gravity works and things like that, that's the bread and butter of physicists, not mathematicians. The question is, was there any other physicist who would have thought the same way as Einstein? There were certainly physicists who had the same mathematical chops that Einstein did, but the physical insight that he had was unmatched since Galileo, basically, and has still been unmatched since. So it might have taken a while, but the tools were there, so I don't think it would have taken too long. Jonathan Bird says, in physics and philosophy, Werner Heisenberg said, the world thus appears as a complicated tissue of events in which connections of different kinds alternate or overlap or combine, and thereby determine the texture of the whole. The word texture is refreshing and sensual. It even feels unscientific, but maybe that is a philosophical problem that Heisenberg is trying to get at. I'd love to hear what you think about the texture of the universe and the role of literary emotional language in describing it. Well, I'm all in favor of literary emotional language. It's too bad that some of the best physicists in the world aren't the best describers or poets or writers in the world. And I think that helps. It prevents a lot of people from really feeling what we physicists feel about the universe in a way that I would like them to be able to do. Having said that, so even though I'm all in favor of that kind of move, Heisenberg in particular, in this particular passage, is trying to sell you something that I don't believe in. This is, Heisenberg was, at least as much as Niels Bohr, the champion of the Copenhagen interpretation of quantum mechanics. And it's an interesting story. John Wheeler was another of Niels Bohr's acolytes. And Wheeler was, despite being Hugh Everett's thesis advisor, Wheeler was really an advocate of the Copenhagen interpretation of quantum mechanics. And Wheeler's famous paper, It from Bit, that's not the name of the paper, but the quote that is remembered from the paper is It from Bit. It makes people think that Wheeler was saying that reality is really made of information. And indeed, there's a whole large effort right now called It from Qubit, where we say, well, it's really quantum information, not classical information that is doing the work. But that's not what Wheeler was on about. That is not his point. His point, being a Copenhagen person, is that what really exists is not a wave function or anything like that. What really exists are the measurement outcomes done by various measurements. Like before you do the measurement, this is a very Heisenbergian point. Wheeler was trying to say, before you do that measurement, there isn't any it, right? And when you do the measurement in quantum mechanics, he tried to make an argument that quantum outcomes are necessarily discrete. That's not obvious because things like position and momentum in conventional quantum mechanics are continuous, but he took as the paradigm the measurement of a spin, and you get a yes-no answer. So John Wheeler knew about quantum mechanics. He could have invented It from Qubit himself, but he didn't because he was making a different point than that. And that's the point Heisenberg is making. When he says a complicated tissue of events, that's not just poetic language. He means measurement outcomes. When you're not looking at it, the thing doesn't exist. That is the Copenhagen point of view, or at least there's no sense of existence that we can objectively talk about. We should only talk about, says the Copenhagen interpretation, the results of measurements. And that's the point that Heisenberg is aiming at here. Henry Jacobs says, multiplying integers is easy, factoring integers is hard. There's a directionality. Can this difficulty be interpreted entropically, and does it have any bearing outside math, such as in physics? I don't actually know. So you say, can it be interpreted entropically? And I guess the question is there a colorful analogy between the two things? Entropy increases. It's easy to go one way rather than the other way. Certain mathematical processes are easy one way and not the other way. Or is there like a really hardcore connection? Can you derive one from the other or something like that? This statement that multiplying integers is easy, factoring is hard, this is a specific example of a more general idea, as I'm sure, Henry, you probably know. But in complexity theory, like we talked with Scott Aronson on the podcast some time ago, one separates problems one can ask into different levels of complexity, and there is the set of problems P that are easy to solve, relatively speaking. There's a set of problems NP, and NP is not defined as problems that are hard to solve. It's defined as problems whose prospective answers are easy to check. Okay, so maybe there are problems that are hard to solve, but it's easy to check and answer. Maybe there's not. That's the P versus NP question. But most mathematicians, logicians, philosophers think that P and NP are in fact not equal to each other, which is a way of saying, I believe there are problems that are hard to solve, but it's easy to check a supposed solution. So that isn't a directionality, an asymmetry between solving and checking in general. And there's other things in math that are like that. Differentiation is kind of easy. Integration is kind of hard. I don't want to say that is the same thing as entropy increasing over time. I don't see why it has to be, but maybe I've certainly suggested myself that they sound similar in some ways. Is that similarity deeper? I truly don't know. Gary Miller says, in your October 2024 AMA, you mentioned James the Just as likely being a real person. Do you think that there was historical Jesus, someone you could meet if you traveled back 2,000 years, or is Jesus primarily a retelling of earlier mythological figures? So James the Just, for those of you who don't know, was Jesus' brother, and he was a leader of the Jerusalem Christians after Jesus was crucified. And there is, enough evidence in the archaeological / historical records to say that James existed, maybe arguably more than Jesus. But of course, that all depends on what you think about the New Testament. The books in the New Testament are not eyewitness accounts. The earliest books in the New Testament were written by Paul, and Paul never met Jesus. Paul never, got to know about Christianity until after Jesus had already been crucified. So there's nothing in the New Testament that is an eyewitness testimony. The Gospels, we believe, are things that were written down decades after the fact. They were passed down as oral traditions before they were written down. So it's not completely crazy to ask whether or not Jesus could have been completely made up. Like there's no such person as Jesus or not, because we don't have eyewitness testimony. But I think that there's plenty of other kinds of testimony. Like unless you believe that all of history is completely unreliable, there's plenty of reasons to think that Jesus existed. There's very little reason to think that any quote attributed to Jesus in the Gospels is very believable, right? These are supposed to be words handed down by oral traditions through decades from person to person. The chance of distortion or even outright fabrication are very, very large. So I would not put a lot of credence in any specific claim about what happened to Jesus or what he said, but I think that he almost certainly did exist. Ramon Van Fleet says, how do you feel about the ethics surrounding NBA player trades? I've always found it somewhat curious that a player can essentially be forced to move to a new state, work for a new employer, and leave friends and family behind without any say in the matter. I get that the counter-argument is that they're millionaires, and if they want to do something else, they can, but it still strikes me as something that wouldn't be legal in almost any other setting. I think it's a reasonable question to ask, but I think there's another fact, in addition to the fact that they get paid handsomely for moving around, which is that you kind of need some system like that. Even though we have individual NBA teams, the kind of money-making entity is the league, not the team. I mean, de facto, that's not true. De facto, individual teams earn money, but one team by itself, without a league to play in, wouldn't earn any money, okay? You need some kind of cooperative agreement among many teams. And as part of having revenues and having competitive balance, et cetera, they have the idea of making trades. I don't think that many players have even argued that there just shouldn't be trades at all. It's interesting to contemplate what that would be like if there weren't trades. There's various ways to imagine tweaking the system. But there are often trades that benefit everybody. As perhaps you know, there's certain times when players demand to be traded, right? And maybe that benefits both the team and the player. So I think the system is very far from perfect, but something like the system makes sense to me. Alexander Kondratsky says, one aspect of quantum measurement has been bothering me, so please correct my chain of reasoning. It seems that measurement collapses or slices the wave function to some eigenstate, but isn't that dependent on a choice of basis? Spin up of an electron is relative to what you consider up. At a fundamental level, how do we force a basis when we make a measurement in a laboratory? Well, the answer is that we choose what it is we're going to measure. So, for example, the classic example of a quantum measurement is the Stern-Gerlach experiment. This is where you send a spinning particle through an inhomogeneous magnetic field. So a straight magnetic field wouldn't do anything, but a magnetic field which is sort of pinched in one direction interacts with the spinning particle in a way that if the spin is up in the direction that you've arranged your magnetic field, then the particle is deflected up. And if it's pointed down, then it's deflected down. And it is a fact of quantum mechanics that you might think, well, what if it's spinning halfway in between? What if it's spinning perpendicular to the magnetic field? The miracle of quantum mechanics is that a perpendicularly oriented spin is a superposition, can be thought of as a superposition of a vertically up and a vertically down oriented spin, and those two components get separated by interacting with the magnetic field. But you chose to orient your magnetic field up and down. You could also choose to orient it left and right or whatever, and that would correspond to measuring a different fact about the spin, the X spin or the Y spin, rather than the up spin or down spin, okay? So it's just a fact of physics, like real physical measurements happen because you have an apparatus and some object that are interacting with the system you're measuring in some very particular way. And what that particular way is and what your apparatus is doing tells me whether I'm measuring the vertical spin or the horizontal spin, or am I measuring position or momentum or whatever. All these different things are measured using different actual experiments. So it's not like the rules of quantum mechanics force it on us. It's our choice of experiment forces it on us. Enrique Ariola says, regarding the second law of thermodynamics, wouldn't black hole radiation be a violation of this law given that black holes have the highest entropy possible, and that their radiation leads to their eventual disappearance, which means that entropy would essentially decrease? So no, because black holes do not have the highest entropy possible. I kind of rant on about this in my first trade book, From Eternity to Here. In fact, I upset Roger Penrose. Roger Penrose was nice enough to blurb the book, but he has made this statement that black holes have the highest entropy possible, and it's not true, and he knows it's not true. They have the highest entropy possible in a given region of space. But when they evaporate, when they dissolve into particles that are radiated away by a Hawking radiation, the particles that carry away the energy are spread over a much larger region of space. And you can calculate what the entropy is of all the Hawking radiation, and it is larger than the initial entropy of the black hole. It's just not squeezed into a small region of space. So I pointed out in the book that Penrose was wrong about this, and he asked me to change the phrasing to be something that indicated that he knew that all along, which is probably true, so I can't really complain. Dave Whipp says, if I pick a few points on the edge of a circle and attempt to draw lines to the center, most likely they will meet at a triangle or some other polygon. It's really hard to draw them precisely to meet at a point. Yet the story of Hubble is that when we observed a handful of galaxies moving away from us, and then plotting the movement in reverse, conclude the universe must have started from a point of infinite density, period. What leads to the conclusion that radial lines must have started classically from a singular point rather than at some region that simply was smaller than today but finite? Is this pop story overly simplified? This is a perfectly good question, and I get to talk about Roger Penrose once again. If the particles in the universe didn't have any forces acting on them, in particular didn't have gravity acting on them, then indeed they would move on straight lines, and it would be really, really strange indeed to imagine we could extrapolate them backward to a singularity. But they do have gravity acting on them. And even in Newtonian gravity, they would come close but ultimately miss each other. But general relativity is different. General relativity becomes stronger when things become very, very dense. That's why you can make black holes and things like that. And so it was Penrose who first proved a theorem. It was extrapolated to the cosmological case by Stephen Hawking. But the theorem basically says if you have enough energy density in a region and it obeys certain conditions that are mathematically straightforward to write down, then you will inevitably have a singularity. This is a feature of general relativity. Now, general relativity might not be right. Who knows, at large energies or something like that, where quantum mechanics kicks in. But I think it is that's why Roger Penrose won the Nobel Prize for proving that singularities in black holes, and also for that matter in the past at what we call the Big Bang, are a prediction of classical general relativity. Philip Rothland says, I asked GPT to analyze all previously asked questions in all AMAs to identify recurring topics and determine your areas of expertise. Based on this analysis, I wanted GPT to generate a fresh, insightful question that has not yet been asked but aligns with your knowledge. Here's the question it came up with. Many of your discussions revolve around AI. However, one aspect that hasn't yet been deeply explored is how AI intersects with emerging fields like neuroscience or ethics. What are some underappreciated insights or challenges at this intersection that you find particularly compelling? So I don't think GPT did a very good job at this one. Sorry, Philip. I don't think it's your fault, but of all the things to ask me about, AI is a weird one, especially because, I have certain things I feel strongly about AI, but many things I don't, because I try to keep track of what I am not an expert in. Specifically, how AI, and also the form of the question isn't the best. This is feeding back to the previous question about, can we ask questions over and over again? This kind of very vague, open-ended question is sub-ideal. It's okay, but just saying what underappreciated insights or challenges do you find particularly compelling? That's exactly the kind of question I'm unlikely to answer because it's a little bit too vague. If you have your favorite insight or challenge that you would like me to comment on, you're more likely to get me to answer that kind of question. I don't know. So the answer is I don't know. So I probably wouldn't pick this question. I'm picking the question because of the cute AI framing of it, but the actual question being asked, I probably wouldn't pick because I don't have anything especially interesting to say about that, especially ethics. I'm not sure why AI would have. Obviously there's questions about ethics of AI, could we imagine building an AI that was conscious and had agency and deserved rights? Those are interesting questions. My answer to that is we can imagine it, but we're not close to doing it. But the existence of AI as being something that we would use to explore ethics, I'm really not sure why that would happen. Colin Small says, you've talked at length about your love for basketball as a fan, but do you play basketball as well? Does Sean Carroll dunk? Can Sean Carroll splash threes? So anyone can splash threes given enough time, given enough opportunities. No, I'm not very good at playing basketball these days. I am of a certain age where my basketball playing days are largely behind me. I could, but it's just that my environment does not lend itself to doing that very easily. I'm not so decrepit that I cannot get out there on a basketball court, but as a matter of fact, it's been a long time since I have. When I was an undergraduate, and even more so when I was a graduate student, I was playing quite regularly. And I was entirely mediocre. I was, in our set of astronomers who made up our intramural basketball team, which I was on. I was not a star, nor was I the worst player on the team. There was no dunking involved, certainly not on the regulation rim anyway. The only interesting thing I can say about that is that there's a chance, and I truly don't know if it's true, but there's a chance that I once played basketball against Barack Obama. I wouldn't have known it at the time, but we had an intramural basketball team, and I was a grad student between 88 and 93. And I think that my first 3 years there at Harvard coincided with Barack Obama's law school career at Harvard. And we definitely played intramural teams from the law school, and he was a basketball player. So it's completely possible that I guarded Barack Obama once, but I have no recollection of it right now. Sorry about that. Ben Lloyd says, you've talked briefly a few times about the idea of bubble universes being a plausible answer as to how we think about this unusual low entropy at the Big Bang. Do you think this hypothesis is not talked about enough? And if so, why? I know Stephen Hawking was a proponent of it, but I don't see many other physicists talking about it. I'm guessing that's due to it being hard to get lots of empirical evidence for at the moment. Also, and maybe this is a silly question, but how does this hypothesis align with other prevailing theories such as cyclic models and inflation? Is there a potential for overlap, or are these theories generally considered to be mutually exclusive? Well, certainly the way that Jennifer Chen and I imagined it in our paper from 2004, we use inflation as part of the story, but it's not a traditional eternal inflation model or a cyclic model for the simple reason that those ideas, again, the traditional version of those ideas, have an arrow of time that points in the same direction for all eternity. So you have to bake it in. You are not explaining why there's an arrow of time. You're just putting it in to your hypothesis. Our attempt was to explain why there's an arrow of time, and the way that we did it was to have the arrow point toward the future and point toward the far, far past, early in the pre-Big Bang scenario. So I think that I would be happy if there was more talk about this scenario, but it is based on highly speculative, ill-understood physics in our particular version of it. I am working on a paper about this scenario right now to sort of push it forward, but there's a lot we don't know. And that's perfectly fine. Scientists will make choices about what to work on. And it's not just because a question is interesting, but also because they think they can make progress on the question. That's a perfectly legitimate idea for scientists to have. I personally think that this question is much more interesting than the average person because I'm very aware of this arrow of time issue that I think other people are not paying enough attention to. Rob Patro says, Doge and the administration have made it clear, I think, that the assault on science is not just an effort to cut costs, but an effort to either destroy science outright in America or to diminish and censor it to such an extent that it becomes unrecognizable, imperiling American scientific excellence and our national security in one fell swoop. As a scientist, I'm somewhat at a loss what to do in this brave new world. My question to you is twofold. What should scientists be doing to help salvage what we can of our institutions and the systems that have made America a world leader? Along the same lines, when and if it does make sense to think about abandoning ship for a country with an administration that doesn't view scientists as the enemy, but rather a national resource. I don't quite want to agree with the premise of the question right away. So I don't think that they've made it clear that it is an effort to destroy science outright in America. I think that's an overly simplistic way of putting it. There's some aspect of it. I mean, there's no question that various members of the administration, most obviously J.D. Vance, the vice president, but others as well, have taken an explicitly anti-academic, anti-intellectual point of view on things. Vance has said professors are the enemy, universities are the enemy, etc. And I think it's unmistakable that certain aspects of university existence and life are looked down upon by the administration. But honestly, I think that you can't undersell the idea that it's not even that intentional what they're doing. What they want to do is cut costs, and there's an attitude that they know better than everybody else. It's a fundamentally anti-expertise philosophy, right? Like the idea that there are people who know a lot about things and should be trusted with the hardest decisions is anathema to the people who are running the country right now. And it's in part a reflection of a Silicon Valley ethos. It's not hard to dig up quotes by Silicon Valley leaders disparaging the idea of reading books in favor of, everything interesting should be put in a blog post or something like that, right? The idea of hard-earned, very careful, expert-level knowledge is just not something that is respected, so they don't see why they should spend all this money on science and education and things like that. It's really just a matter of whipping the workers to work harder. That's what we really need, right? So, of course, de facto, these align. At the end of the day, you end up destroying science, destroying trust in science, destroying trust in the United States from scientists abroad, and so forth. As far as when and if it makes sense to think about abandoning ship, you can always think about it. That's a very personal decision. As I've said before, my inclination is always to stay and fight and to try to make things better, but you can imagine things becoming so bad or, opportunities arising elsewhere that you might want to do that. I can't offer any individual advice. What can scientists do? I honestly don't know a lot. We're not a lot of the electorate. I think that we can try, I guess the reason I'm hesitating is because there's obviously things to do, but they're all kind of vague and none of them are immediately effectual. I think that scientists need to get more support from the world. We need to be a little bit less insular and focused on talking to each other and more devoted to talking to people outside, both science, but also academia or our political perspectives or what have you. People on the street need to be convinced of the importance of science and to be convinced of the importance of intellectual life more broadly. Scientists are just as able to have internecine battles, disparaging other departments in the university as anyone else is. And I think that we need to understand that we are on the same side overall in this. And I think that we need to reinvigorate not just respect for education, but also education. We need to make higher education cheaper and more prevalent so that people understand what's going on a little bit better. Part of that is as straightforward as decreasing the debt that students come out of college with, right? Making it more accessible by letting more people in and letting it be more affordable to more people. And then, of course, I think that, universities can't, as people have very often said, cannot acquiesce prematurely. There's this very, very embarrassing thing that just happens with Columbia University. You might know that Columbia was at the center of accusations of anti-Semitism because there were protests on Columbia's campus against Israel's war in Gaza. And, I did not follow that very, very carefully myself, but I have zero doubt that some people at some point involved in those protests said anti-Semitic things. And I'm not in favor of being anti-Semitic or supporting anti-Semitism. I am in favor of allowing protests on campus. And so it's the university's job to balance these values and allow people to speak their minds without being threatening or racist or anything like that. So Columbia had a lot of protests, and for whatever reasons, again, I don't know, I haven't been following it too carefully, they were the epicenter of criticism by Republicans in Congress for allowing these things to go forward. And so the university, so the administration just canceled or threatened to cancel. You never know with this administration whether they're actually doing something or just blustering about doing something. But they threatened to cancel $400 million worth of grant money to Columbia. And in response, Columbia basically completely folded and said, oh, well, we're sorry and we'll try to do better. And I think that it's just a strategic mistake. It's both a values-based mistake. We shouldn't be those people. We should be better than that. But it's also, as an absolutely practical matter, a mistake because it's not like the people who are trying to cut money to universities will hear you grovel and say, oh, okay, I changed my mind, you get your money back. There's no amount of groveling that will get the money back. So a long-winded way of saying, I think universities need to stand up. They need to be very, very clear about their support for free speech, for intellectual inquiry, for science, for the humanities, for everything else that we're supposed to stand for as institutes of higher education. Will that help? Maybe it will help down the road. I don't know what the short-term effects will be. Mark V. says, you've mentioned that advanced civilizations could try to make contact through long-lasting objects. Imagine such a civilization had visited Earth around the time land vertebrates with eyes had evolved. They also determined that our moon was a promising geologically stable location to place such an object. Moreover, the civilization was capable of modifying the surface of the moon to draw a large-scale message that would be visible from Earth. Assuming they prioritized geological stability and long-term visibility, what kind of symbols or patterns might they create to ensure their message is noticeable as intentional communication? Well, it wouldn't be that hard, right? I mean, you could just write a bullseye or a little, cartoon image of an atom or something like that. Or you could be more clever and do something like we had on the Voyager spacecraft, right? The golden record thing that tried to have little symbols representing where we are in the cosmos and things like that. So there's many things that you could do. But I think that that's not really the way that I would think. I think that's a pretty kind of dumb way for the aliens to leave a message for us. I mean, remember, it's hard to conceptualize this, but we're imagining civilizations that are enormously more technologically advanced than us. They could do better than paint the moon. They could invent infinitely long-lasting machines, self-repairing, running on solar power, et cetera, that could repaint the moon every 3 days, right? That could send us signals in all sorts of ways. Again, I think that whatever the aliens wanted to do, they could do it. So either they haven't done that, or they and this way that I'm thinking of, could be triggered by certain signals in the Earth, global warming, or the detonation of nuclear warheads, or radio waves indicating advanced technology, right? I mean, there's all sorts of ways that they could trigger some machine that they had left behind in the solar system to sort of come to life and give us messages. So either they haven't wanted to do that, or maybe they're waiting for more advancement than we have. Maybe they have a little trigger that says, wait until we hear radio waves and then wait another 10,000 years. Right? Who knows? I really don't know. But I think if the aliens want to talk to us, it wouldn't be hard to notice. Benjamin Zand says, do you have any plans to host or organize another Moving Naturalism Forward seminar like you did in 2012? We know you're busy, but you can count on support from Mindscape listeners. Yeah, that's something that would be one among many, many fun things that one could do. I don't have any plans to do that. For those of you who don't know, in 2012, we got together a small group of people in Stockbridge, Massachusetts. And the idea was to get together people who were naturalists in many different fields, naturalists in the sense of not like studying plants, but not theists, okay? So basically atheists. And rather than talk about, ways of combating theism or intelligent design or whatever, it agree that we all are on the same boat and the same track with this particular question, but there's still questions that remain unanswered that we need to think about moving forward with. So we talked about consciousness and free will and morality and things like that. I think it was quite a success. I mean, maybe you can always be more successful. We didn't ask anyone to write a document or a paper or anything, but we did videotape everything, and they're all quite well edited and on YouTube. For whatever reason, the YouTube videos never took off. They never got a lot of hits. I will try to remember to put a link in the show notes to the Moving Naturalism Forward videos. But doing it again, well, it was a special event. There are people there who are no longer with us, like Dan Dennett and Steven Weinberg. And it would be a different group of people, obviously, but I think there's other things to be done. Like I did that. In fact, David Wallace and I have talked a lot about a Moving Everett Forward conference where we get people who are you're only allowed to come if you're a believer in the Everett interpretation of quantum mechanics. And we admit that there's lots of questions unanswered yet, and we work on answering them. Who knows whether that will happen? There's a lot of things that we need to do. Ask me after I've written a few books. I got to get those done first. Tom S. asks a priority question. I've been bothered by this question since the early 90s. It involves special relativity. Given that a photon does not experience time, it should also be that the distance traveled from the photon's frame of reference is zero. In essence, to the photon, it is simply jumping from one atom to an adjacent atom. Since no time elapses for the photon since leaving the source atom and being at the destination atom had to be fixed when the photon left the source. So from my frame of reference, I walked into my backyard at night, stare up into the sky, and a photon from a star 1,000 light years away strikes my eye. That would suggest to me that there is no free will. I had no choice but to be born and walk out that night, so the atom in my eye would be the photon's adjacent atom when it left the star 1,000 years ago. Is my reasoning flawed, or is there no free will? If flawed, where did I go wrong? So there's a few flaws in the reasoning, but the big leap is to questioning about free will, which is a whole different kettle of fish. So just to be clear about the setup, where is the sentence that I'm thinking about here? Since no time elapses for the photon between leaving the source atom and being at the destination atom had to be fixed when the photon left the source. What does the word when mean in that question? Because this is the whole point of relativity, is that dividing up space-time into space and time is different for different observers. What you mean is, in the photon's frame of reference, the atom is in the same time in some null coordinates as when the photon left the source, but not in mine, right? Not in the frame of reference of the thing that emitted the photon in the first place. There, the thing was set up long before it was absorbed, okay? So this is a perspective, relative question, and different people are going to say different things about it. Really, I think the issue here is not anything about special relativity or photons. It's just about determinism. If you believe that the world is deterministic, then you know what happens now, and you're going to be able that what happens now will enable you to predict what happens in the future. Even as an indeterministic person, since I think that quantum mechanics exists, I am a block universe person, so there is a fact of the matter about what will happen in the future, even though I don't know what it is. And then, of course, the question is, does this have any bearing at all on the question of free will? That's a longer conversation that I've talked about many different places. But I think of free will as perfectly compatible with determinism because I'm a compatibilist. I think that free will is a higher level emergent phenomenon, at least in the way that I think about people making choices. If you want to define free will as the ability to violate the laws of physics in a libertarian sense, then I don't believe in that. So you really I would suggest, if you care about these questions, really dig into the issues of compatibilism and the meaning of free will. Talk to or listen to the podcast I did with Janan Ismail or Dan Dennett or one of the various people that we went over that question with. Kelly Hoogland says, I was listening to an episode of Radiolab, which is a science storytelling podcast. In this episode, they were briefly explaining quantum entanglement. Without giving you any direct quotes, given that the words observer or superposition were not used once, how good a job could they have done? I think you didn't give me quite enough information to tell you how good a job they could have done. Certainly, if the question is secretly, can one adequately explain entanglement without using words or equivalent words to observer and superposition, I don't think that the word observer or observation or measurement plays any role at all in explaining entanglement. I don't think that's what entanglement is about. But I would think that, since I am an Everettian, and Everettians don't think that measurements or observations are special things. It's all just a wave function obeying the Schrodinger equation at the end of the day. The word superposition is harder to avoid when you're talking about entanglement. To explain entanglement, when I explain it, I first have to say, if there's a spin, a particle with spin, it can be in a superposition of spin up and spin down, for example. And if you have two spins, it's not true that they are just separately in superpositions of spin up and spin down. They are in superpositions of they can be entangled superposition, which means that if one of them is up, the other's down. If the other one is down, if the first one is down, the other one is up. So could you explain that without using the word or concept of superposition? That would be very, very difficult. I mean, somehow to explain entanglement, you have to get across the idea of what a quantum state is. That's why observations don't matter. It doesn't matter how I observe the quantum state. What really matters is what quantum states are. And you don't need to use the word superposition in explaining what quantum states are, but given that we usually start by thinking about classical observable phenomena, it is traditionally easiest to talk about superpositions when we do that. Rory Cochran says, I keep coming back in my mind to what I feel like is a clash between your December 2023 immortality address, in which you conclude that humanity is doomed because the universe is headed for a heat death in de Sitter space, and David Deutsch's ideas in The Beginning of Infinity, in which he says words to the effect that any problem can in principle be solved once the knowledge of how to do it is discovered, with the only limit being whether or not the solution is prohibited by the laws of physics. My issue is, can we say categorically that there is nothing that could ever be done about the looming heat death of the universe? Can we say for certain that humans or intelligent life could never work out some novel piece of universe, some engineering perhaps with elegantly placed black holes or little big bangs or something? If we can't rule it out, then there's hope for immortality yet. Well, I hope that if you are a longtime listener of Mindscape, you know that questions about categorically saying things and being certain about things are always met with, no, we cannot categorically say things. We cannot be certain about things. That's just not how the way things work. We can make provisional statements subject to certain assumptions. So if you assume, as I tried to assume in the talk about immortality, that we really are going to live in de Sitter space with a forever eternal cosmological constant that will never decay, and you assume that our understanding of what it means to reach equilibrium in a thermodynamic system is more or less correct, and you agree that thinking in any real substantive sense increases entropy and requires an out of equilibrium condition, then it is just a fact that the laws of physics, even up to David Deutsch's way of thinking about it, prohibit immortality in this universe. Now, of course, all those assumptions could be wrong in one way or another. After all, we could be living in a simulation for all we know, right? And we might think of it as very unlikely, but could be. It's possible. It's possible the cosmological constant will go away. It's possible that the universe will recollapse. Who knows? There's many hopes that you could hold out for, but I'd like to think that it's useful to think through our best understanding of the universe and to try to figure out what is compatible and incompatible with that understanding, even admitting that that understanding might need to be modified someday. Erminio Maganzini says, the gravity waves we have detected have been created by the collision of black holes and neutron stars. Are these the only objects that produce gravity waves, or are these the only objects that LIGO can detect? That is LIGO incapable of detecting weaker waves? Mostly it's incapable of detecting weaker waves. There's plenty of other ways to make gravitational waves, but it's not just a matter of weakness. It's also a matter of frequency, right? Just like there are telescopes that look at visible light and different telescopes that look at radio waves and different telescopes that look at X-rays, gravitational wave observatories have a bandwidth. They have a region of the gravitational wave spectrum to which they are sensitive. So, for example, we are pretty sure that there's lots of gravitational waves being made by spinning neutron stars or spinning white dwarfs for that matter, possibly by supernova explosions, almost certainly by medium-sized black holes spiraling into supermassive black holes in our galaxy and elsewhere. We think that all these are out there. There might even be a cosmic gravitational wave background from the early universe, for all that we know. But LIGO is just not sensitive to the relevant bands for those kinds of things. I think we have a shot at the supernovae. I forget, actually. But LIGO is sensitive to, relatively quick gravitational wave frequencies. So you need to pack a lot of matter and energy into a relatively small region of space to have it move quickly enough to emit those frequencies. And you also need it to be heavy enough to give off gravitational waves that are detectably strong. So if you put those two requirements together, relatively quick and therefore small, but also very, very massive, you're more or less left with in-spiraling black holes and or neutron stars. Ethan Richardson says, in the midst of all the real-world turmoil and horror, how about a softball I've been meaning to ask since I learned your cat's names years ago? As a lifelong Shakespeare fan and one lucky enough to have had the opportunity to play Caliban as a senior in high school, I'd love to know more about your own relationship to his work. Things such as your favorite plays, quotes, is he really the GOAT, the greatest of all time? And if you care to weigh in as a good Bayesian on why some folks are so invested in the notion that he didn't write his plays. So yeah, Ariel and Caliban, as many of you know, are named after characters in The Tempest by Shakespeare. Puck is also named after a character famously in Midsummer Night's Dream. And Shakespeare, is he the greatest of all time? I think that he has a better claim than anybody else, okay? But I would absolutely respect people for thinking that they like somebody else different. I don't think that there is an absolute ranking of greatness in authors. Shakespeare is kind of special, I think, kind of unique in his ability to write poetic language that is just very vivid and imaginative, and especially in coming up with new words. I once went to a performance of Hamlet in Washington, D.C. by a Russian theater troupe that specialized in silent performances. So they had a version of Hamlet with no words. And, it was fine, but a lot of me is thinking like that's entirely besides the point. Like, Shakespeare is not celebrated for his plots. That's just not his strong point. I mean, they're pretty good. Some of the plots, they can be heartbreaking in sections, etc. But really, you're there for the language. And when you literally take away the language, I think that you're probably not showing off the plays in the best light. Favorite plays and so forth. I like The Tempest. I like some of the classics, Macbeth and Hamlet and so forth. I find Othello heartbreaking, too much to really enjoy. Julius Caesar is one that I really like. I was exposed to that relatively early. I like the dramas more than the comedies. I think the sort of slapstick comedy of errors, mistaking twins for each other kind of thing that Shakespeare loves in his comedies are not my style. So I'm a drama kind of guy on that. Why are some folks invested in the notion he didn't write his plays? Yeah, people like conspiracies and fun mysteries and things like that. There's no good evidence for it. I mean, maybe there is some argument, not for Shakespeare not being the author of his plays, but for why people are so interested in it. There is sort of an almost class-based argument because Shakespeare was relatively uneducated. He was somewhat educated, but he wasn't like super aristocratic hoity-toity. And there's a certain set of people who think that he was so good with language that he must have been aristocratic and hoity-toity. So they want to attribute his plays to some aristocrat. Obviously, I don't think that's a very compelling logical train of thought there. All right, my voice is going, as you might notice here, so we're going to reach the end. We're not quite at the end yet, but only a few more questions left. Mark Scheuern says, do you still have your BMW i3? In general, has your experience with an electric car been good? Yeah, we still have the i3. It's convenient. It's perfect for our purposes, which is that we have two cars, and if we really need to go a long way, we can get in the gas-powered car. The i3, for those of you who don't know, is a tiny little car. It's very, very well designed so that it's actually pretty good space inside, even though it's tiny on the outside. It's kind of similar to a Mini, if you know what that looks like. And it was always meant as a tootling around town car. It was never meant to take you very far. It's for commuting and things like that. So Jennifer and I don't drive very much. She works from home. I can walk to work, right? So we don't need a car to take us very far. And the i3 is perfect for getting around town. It's the car we usually drive from place to place. And also they had fun. Like, I don't know what happened, but the BMW designers, when they decided to enter the electric car game, had fun with it. They came out with two cars, the i3, which is like this little tiny thing that maneuvers really great and it's kind of fun to drive because it's so sporty and interestingly designed from the inside. Like, our i3 has a interior design package that uses carbon fiber and fabric and vinyl and metal and everything, and it's just very, very interesting compared to the vast majority of interior car designs. And then the other one they made was the i8, which was like this hyper sports car kind of thing, which apparently was very expensive and very, very difficult to get in and out of. So I never have driven one. I don't know. But then, they canceled both of those and are now making a very bland selection of BMW sedans and crossover SUVs, just like everybody else. So what can you do? The electric car experience itself has been wonderful. You don't need to go to the gas station. We just charge our car in our garage every night, so we don't even need to worry about charging stations or anything like that because we're not taking it on road trips. There's a certain amount of, it's a relatively new technology compared to internal combustion engines, so we've had to get the battery replaced, even though there's less than 20,000 miles on the car. But overall, very, very happy with that. I'm hoping that given how little we drive it, it will last another 20 years easy. Funky Town says, in episode 305 with Liliana Mason, you talked about media provocateurs stoking anger and leveraging status threat to get people to vote a certain way. I'd like to know if you have an opinion about some of those big-name pundits as to whether or not they actually believe what they are saying, or rather driven by ego, wanting to be influential, monetary gain, or something else entirely. Well, it's kind of a vague question because, of course, the category of big name pundits covers a lot of ground. And, I think that I would prefer to not if I can avoid it, attribute bad faith to people whose job is punditry. Like Ezra Klein is someone who we had on the podcast, and I think we had a very interesting discussion of the origin of polarization. And he is very big in the pundit game right now. And sometimes people on the more or less liberal side of the ledger, who Ezra is also on that side of the ledger, but they accuse him of being too sympathetic to centrism in various ways. And I think that's literally just who he is. I think he's always been that way. I've known Ezra for a long time because he and I joined the blogosphere near the same time in the early 2000s, and we both had relatively small time blogs, but there weren't that many blogs, so we read each other. And he was very young at the time, obviously, and he just always was like that. He's not making it up to get more clicks or a better job or anything like that. He's an institutionalist by nature. He's a liberal institutionalist, but nevertheless an institutionalist. And I think that a lot of people who are big name pundits are like that. They're not really playing a game. They're showing you who they are. Not everyone. Of course, some people are entirely cynical, etc. Believe me. But I think that your first guess should be that people are just being honest. Now, some people are notoriously inconsistent or hypocritical. But again, I think that your first guess should be is that that's just who they are. Like, they don't have coherent thoughts in their brains, and they're saying one thing one day and something else the other day, not because they're especially cynical or for monetary gain. It's just at the moment they think that's true, right? That's not true for everybody. That's not the case for everybody. But I think that should be your first. Your priors should be large, that is what is going on before we leap right to associating nefarious purposes to what people are saying. Bran Muffin says, could ER equals EPR be established to the same level of rigor as ADS-CFT? What implications would such a proof have for the field? So for those of you who don't know, ER equals EPR is an idea that connects the geometry of space-time with quantum entanglement. And it came out, it's due to Juan Maldacena and Lenny Susskind, and it came out in the context of ADS-CFT, the boundary bulk correspondence, relating holographically field theory without gravity to a bulk theory in one more dimension with gravity. And so what Maldacena and Susskind noticed is that if you have basically two copies of an ADS-CFT, right? So you have two CFTs, and both of them could, depending on the quantum states inside them, have a bulk anti-de Sitter space emerge holographically. But if you entangled the two CFTs, if you entangled them by a lot, what you would see is essentially a wormhole connecting them. That would be the single emergent geometry. So ER is Einstein and Rosen. Those were the folks who first really wrote about wormholes in the context of the Schwarzschild solution. This is back in 1935. And then EPR is Einstein, Podolsky, and Rosen, same guys plus Boris Podolsky writing about entanglement in the same year, 1935. So two papers in the same year by almost the same authors with nominally nothing to do with each other. And Maldacena and Susskind said maybe they do have something to do with each other. Maybe in a holographic sense, there's some connection between entanglement and the geometry of space-time, in particular wormholes. And they extrapolated it boldly, like great scientists will do. And they said, if I just have two particles entangled with each other, maybe there is some sense in which there is a microscopic, non-traversable wormhole connecting them. That's the ER equals EPR conjecture. So I really haven't followed the details of discussion of ER equals EPR a lot. So don't trust my impressions, but I'll give you the impressions that I have from sort of halfway knowing about it, which is that it works really well if you have a huge amount of entanglement, as in the original construction, with an entire field theory entangled with a whole nother field theory where we understand the ADS-CFT wormhole that would connect them. It's much less clear what the conjecture even is when you have just a tiny amount of entanglement, like one particle entangled with one other particle. It's not supposed to be like there's a wormhole that you could literally travel through connecting these two particles. So it's not clear to me what it does mean. And there are other people who understand it much better than I do, so we should ask them. But I think that it has led to people thinking about entanglement and geometry in interesting ways. Yes, we would like to have a rigorous, well, you say, can it be established? I think it's not even a matter of establishing it. It's a matter of defining it, of formulating the conjecture in such a way that it could even be checked rigorously. But I don't think that we have that firm foundation or are close to it right now. All right, final question is from Marie Roscu, who says, you said several months ago on Robin Ince's BBC podcast that looking at the Milky Way can make you dizzy. I wonder if you have ever felt dizzy or anxious or even depressed out of too much knowledge. I'm in my 40s and have always loved to study. I have just finished your book, The Biggest Ideas in the Universe, Space, Time, and Motion, and jumped straight into the quanta and fields, and I find it so fascinating. But then people like my mom often tell me that one day I will go crazy as a result of all the knowledge. So, two things. One is the Milky Way making me dizzy is really a straightforward physical response, not a, wow, the cosmos is so big kind of response. It's not about thinking. It's about, like, I am on the edge of a giant disk that is spinning. And I know intellectually, of course, that it's spinning very, very slowly and I shouldn't be dizzy, but there you go. You know, the mind is a mysterious thing. As to whether or not you should be dizzy or anxious about too much knowledge, I am certainly in no danger of that. I know nobody on earth who is in danger of being overly anxious or depressed by knowing too many things. I tend to think that it's mostly the other way around, that people become anxious because they don't know enough things. The number, no matter how many things you learn, the number of things that you don't know, the things that you have yet to learn, is always enormously, enormously greater than the number of things you know. So even if you're worried that someday it is possible to know too much, I am here to tell you that day is nowhere close, and it is not something you should worry about. Worry about not knowing enough, not about knowing too much. With that little message, I don't know if that's an optimistic message or not, but we're going to call an end to this month's AMA. Thanks again, everybody, for supporting. As always, we appreciate it here at Mindscape World International Headquarters. We'll talk to you next time.